Mm. Sir, Srinivas sir, are you there, sir?
Yeah, I'm here.
Okay, sir. We'll be starting, sir.
Okay.
Dear participants, a very good afternoon and warm greetings to everyone who joined us. So, I'm Dr. Kasim, Associate Professor in the Department of EEE, Vishnu Institute of Technology, Bhimavaram. So, welcome you all to the final and concluding day. It is day 6 of our Atal FDP, which is on emerging trends and future prospects in advanced energy conversion technologies and applications. So, over the last 5 days, we have been privileged to hear from some of our finest experts from IITs, NITs, CEA, ORF America, and now from PDSL UK. So, today we conclude our technical sessions with 3 power-packed lectures, followed by the online test, feedback, and the valedictory ceremony. So, with this, the today's expert and by today's session is Dr. Srinivas sir, who has a rich global experience in EV power systems, energy modeling, and battery management systems. I request Dr. I. Kasireddy, coordinator of the FDP, to introduce our resource person. Over to you, sir.
Thank you, Dr. Reddy Kasim. So, Dr. Srinivas holds a PhD in electrical engineering from Vellore Institute of Technology, specializing in electric vehicle battery management systems. He has over 14 years of experience combining academic research and industry practice, including 10 years in academia and 4 years in EV industry. Currently, he serves as subject matter expert at PDSL UK, where he has deputed as a 12-volt battery lead engineer for JLR, contributing to the design and development of advanced battery management system. His area of interest includes battery diagnostic, powertrain design, lithium-ion battery, SOC estimation, active cell balancing, thermal management, and converter design. Dr. Srinivas has published over 20 research papers in reputed SCI and Scopus Index journals. Known for his strong R&D orientation and passion for EV innovation, Dr. Srinivas continues to bridge the gap between academy and industry by advancing sustainable electric mobility technologies. Welcome, sir.
Thank you, Dr. Kasireddy, for the nice introduction. So, dear participants, please join us in warmly welcoming our today's expert, Dr. S. Srinivas sir. Dr. Srinivas sir, thank you very much for accepting our invitation and being a part of this Atal FDP, sir. Thank you very much. And over to you, sir.
Thank you, Dr. Kasim and Kasireddy garu. Let me share my screen.
Yeah.
Yes, sir.
Please confirm me my screen is visible.
Yes, sir. Visible, sir.
Yeah, thank you.
Sir, just change the slide, sir.
Okay.
Yeah.
Okay.
Yes, sir.
It's
Moving.
changing.
Okay, thank you. Okay, thank you everyone. So thank you for inviting me this opportunity where we can share our industry experience with the academics and the students and the research scholars, those who are interested in the various domains of the electrical and electronics engineering related. So my focus, I have the expertise in the battery management system. So I would like to share my knowledge with you people on the battery management system. So let's begin. So we can start. So first, what are the contents I'm going to be sharing with you? So I'm not going in detail much on the all topics, but a few topics I would like to introduce you. So which can help you to understanding the what exactly we required and why we are going through these topics, and what are the exactly the trends or the market, or what is looking from the upcoming researcher or the academics persons to fill the gap between the academics and the industries. So first we will see what is the electric vehicle, why we require this electric vehicle, right? And what are the major components in the electric vehicles, and which type of batteries is available in the market, and how to select a specific battery for the each application. So what are the parameter we need to look into that. Then we will go to in deep about the battery management systems. So if you time permits, I will show you the some EV charging systems and international standards also, and overview of the EV charging models. Then I will take your questions. If you have any questions, you can also post in a chat. We can answer at the end of the session. Let's begin. So why we require the electric vehicles? So first one. So if you look into that, so the electric vehicle requirement, everyone is saying that okay, we need to reduce the carbon emissions, so we need to convert from the conventional vehicle to the electric vehicle. So here I've shown you the one graph which is indicating on the y-axis for your carbon emission, that is CO2, which is emitted by our conventional vehicle or the battery electric vehicle. Okay, there is two types of conventional vehicle as of now. We are using the petrol or diesel. So one is for the petrol vehicle, other one is for the diesel vehicles, and other types we have electric vehicles, right? So where this carbon emission is coming, this we are dividing into the three component. Okay, first one is when the vehicle is manufacturing or production, and after its lifetime. In our India, most of the vehicle its lifetime is 15 years, 15. So after this 15 years, we need to do the disposal. Right. During the disposal also, we are getting some carbon emission because there is a multiple types of materials used inside this any vehicle. Okay, either maybe conventional vehicle or electric vehicle, like rubber tires as rubbers, so aluminium, iron, and leather cushions. So different materials we will use. So this all different metal providing a different kinds of carbon emissions, right? And second one is during a fuel production. So to run this vehicle, we required some fuel, right? Either maybe diesel or petrol. If it is electric vehicle, we required some charging the battery. Okay. On the third emission caused by these vehicles is the carbon exhaust emission. That is when these vehicles are running on the road, these vehicles are exhausting some emission. Okay. If you see in this graph, if you see the diesel or petrol, this should be petrol or this should be diesel. So most of the conventional way, if you see the way during a manufacturing, if you can observe, there is a 50 grams per kilometer of carbon emission is caused by the either diesel or petrol vehicle, right? And similarly, so the vehicle manufacturing or production or disposal, so this electric vehicle batteries, so electric vehicle batteries are emitting nearly 75 grams per kilometer. Okay, this 75 grams per kilometer change. So this is a 25 grams per kilometer. There is a difference. This difference is mainly due to the battery which we are going to be using inside the EVs. Okay, you know that the electric vehicle, any battery is a composite of some chemicals. So due to that chemical composition, so when they are going to disposal or when they are manufacturing the batteries, so it's going to be producing more carbon emission compared to the conventional vehicle. If you go to the second carbon emission, that is a production, fuel production. So this petrol or diesel is a byproduct of the crude oil, right? So we are separating the crude petrol or diesel from the crude oils. So during that process also, it's going to emitting some of the carbon emission. This is for diesel and petrol. It's nearly the 30 grams per kilometers of carbon emission is caused by these diesel and petrol products. Where if you can see, to run the electric vehicle, we require the power supply. So this power supply we are getting from the three different types of. So just if you can only 30, but if we see the pure electric vehicle charged by the conventional electric supply, that is in our home, most of the you know that thermal power station in our India, we are getting the most of the power supply from the thermal, right? This is a non-renewable sources. So this carbon, when we are burning the coal, is going to be, we are emitting the lots of carbon compared to the even from the crude oil separation. Okay, you can see this. This is nearly the 200 to 250 grams per kilometer of carbon emission we are causing to charge the electric vehicle battery. So we need to reduce this one. So how can we reduce? So one way is we can do the hybridization, that is mixing with the renewable energy and our conventional electrical power supply, which we are using currently. Okay. So like we cannot change the entire system at the same time, right? So it's very difficult to change the entire conventional power system to the renewable energy system. So you can integrate some of the system where we are going to charge. Example, at your schools, colleges, offices, or some public charging places. There we can install some charging stations which can charge by the renewable energy. So when you are home, you can charge with your conventional power supply, or you can also at home also you can install your renewable energy source like solar panels. This can be specifically used to charge your electric vehicle. So in this way, by mixing these two into the some good amount of renewable energy and conventional, we can reduce this carbon emission due to the charging of the electric vehicle battery. That is from 250 to nearly only 100 grams per kilometer. We need to reduce further, then we can do, the only thing is we need to reduce the entire, we need to charge our entire vehicles with the renewable energy sources, right? So even if we are using renewable energy sources, we have a nearly the 20 grams per kilometer of carbon emission. Why this carbon emission is happening? Because to run this electricity, we require to manufacture the PV or EVs, or sorry, in the windmills or anything. So this is also causing some carbon emission. So the maintenance or manufacturing both. So this is nearly approximately some 15 to 20 grams per kilometer of carbon emission is causing. So in this way, we can reduce the carbon emission. But by only converting a conventional vehicle to electric vehicle, we are not changing the we are not reducing the carbon emission, right? If you can see here, where when this diesel or petrol vehicles are running on the road, this is emitting the nearly the 150 to 100 grams per kilometer of carbon emission. This portion we are completely removed by using the electric vehicle, which is running on the battery. Okay. Okay. I think maybe it is clear for you. So why, how can we reduce the carbon emission by using the electric vehicle? So how much of impact we can create by using this carbon converting from conventional electric vehicle? So one basic simple example is, so before the COVID, so there is one image was taken at the India Gate during a lockdown. That is on the November 19th, you can see on the same place half picture before the COVID and during a lockdown. So when there is a lockdown, there is no vehicle was allowed to on the road. You can see this much of clear whether we can convert by using the electric vehicle, because this entire portion which is carbon emission is happening on the road, we are completely removed. So what we can do, we need to convert from conventional to electric vehicle to reduce this carbon emission. So if you go to the automobile industry, as I mentioned, so there is a two major vehicles, types of vehicles now in the market. One is internal combustion engine, which is petrol or diesel vehicles. So other one is the electric vehicle. So in this electric vehicle, there is a different types of electric vehicle. One is battery electric vehicle, other one is fuel cell electric vehicle, and hybrid electric vehicle. In the hybrid electric vehicle also, we have a micro hybrid electric vehicle and plug-in hybrid electric vehicle. I will explain you some more bit detail in the upcoming slides. So there we can see what is the difference between these two. So these all are like the energy which we require to run the motor that you can use. Okay. If you go to the battery electric vehicle, it is also called the BEV, battery electric vehicle, or the electric vehicles. So more frequently it's called the EVs in our market. So full electric vehicle is recharged by the main power source is the battery here. So here the traction purpose we will use the battery, and for the traction function we'll use the motor generator. So why we are calling it as a motor generator? So most of the cases to run the vehicle we will use a motoring operation. So we will use some regenerative braking system inside the electric vehicles. That regenerative braking when we are using, so it can use as a charger for the battery. So during that time, we will do some generator option. That's why we're calling it as a motor generator. So this motor generator action we are giving to the transmission system. So to the transmission system, we are converting this rotational energy to the here. Okay. If you go to the hybrid electric vehicle, so there we have a fuel cell and the battery. So here the both energy sources. If you go to the conventional, instead of battery, we are using the fuel. That fuel is used in going to the inside the engine. The internal combustion action will happen. That due to the internal combustion action, then we are going to create some pressure which is going to use to rotate the engine. That rotating energy is converting to the transmission energy in the transmission system. So hybrid, what we will do, generally we will use both the system, fuel cell with the engine as well as battery electric vehicle. So both the energy we are giving to the transmission system. So sometimes when we use the hybrid electric vehicle, what we can do with this transmission system, we can charge our battery directly. So by using the different technology we have now in the different hybrid electric vehicle, where some part of energy when the battery is not in operation, then we can charge the batteries. So whenever we are looking for some change, so in our mind first will come what is the advantage, what is the disadvantage of this change. So if you compare the IC engine and electric vehicle, the main comparison currently is its expensive. The price of the electric vehicle is bit expensive compared to the conventional vehicle. This is the reason. So most of the companies still they are manufacturing the conventional vehicles. So and they started. So we can say almost all major companies, those who are manufacturing the IC engine cars, so they are now they manufacturing the battery also. But still, due to the limited resource of the batteries. So here the most of the problem with the manufacturing or the industries is they don't have a battery technology. So these companies, what they will do, they will took the batteries from the some other companies which they are only purely manufacturing the batteries. So this like if you go to the any Tata or Jaguar vehicles or any company, so what they will do only manufacture the vehicle. They won't manufacture the batteries. They will import the battery from the different places, either China, America, Russia. So wherever these minerals are available for the batteries, so they will importing their minerals and they are manufacturing the batteries and they are supplying to the car manufacturers. So due to that reason, the price is bit high. And out of this price also, most of the 60 to 70% of the cost we are paying for the EV is only for its battery. And second one is running and maintenance cost. So if you are using your two-wheeler or four-wheeler, so you know that. So there is a lots of oils we are using. So brake oil, engine oil, coolant oil. So this kind of oil things we don't require in the EV. We require only the coolants. And the running cost of the vehicle is very less. I will show you one example also. So how much of cheap when we are running cost of the EV compared to the IC engine, it's almost 100% less. If you're spending 100 rupees for the in IC engine to run for 5 kilometer or 10 kilometer, for the same distance, we are spending only the 3 or 4 rupees. Instead of 100, we're spending only 10 rupees. And some states and central government, there is some schemes also there. They're providing the some tax exception, road tax exception, or the for the two-wheeler or four-wheelers. And other one is so for the maintenance here, the one disadvantage is we can say, but currently disadvantage for the people those who are already doing some service work or some technical works on the IC engine. But the educated people, those who are looking for some industrial services, those for people to do the any kind of services or the repairs, we require the well-trained and the educated people. We cannot open it. So if you go to the any roadside, we can find out that some small shops there, anyone can do the repairs, but with the basic training. They can remove your IC engine, they will do service or any oil, anything kind of repair. But in the EV, it is not possible because the battery which is we are using as a energy source, that is a very highly dangerous. If without knowledge, if you are doing to operating, then may possibility they will damage or there is explosion chances. So due to that, you have to must require some well-trained person to do the service and repairs. So because of that, the service and service are also bit expensive compared to the IC engine. And the insurance for the EVs in the current market a bit high, bit compared to the IC engine car. The reason behind this, still the insurance companies are not trusting the batteries. They are saying it's more dangerous than compared to the IC engine, so that's why they're charging a bit more. But as the technology will more improve furthermore, then they will reduce these costs also with more efficient. And next one is the comparison is pollution. So as I mentioned in our first slide itself, so on road, so EVs is producing almost zero, but it will increase the demand of the electricity generation, which is one of the major issue for this pollution. So if we are using the renewable energy sources to charge the EVs, then we can reduce this pollution also by using this renewable energy. Energy efficiency. So this is nothing but a converting onboard energy propulsion. Like, so how much of energy we have, we are getting inside the vehicle, and how much is delivering. This is called the well-to-wheel concept. So energy efficiency comparison. I will explain you in the next slide. So in a conversion energy in the EV is more compared to the IC engine. There's nothing but if you are using a 1 liter of petrol or something, but when we are converting that into the IC combustion engine, is going to be combust and it's going to converting into the some heat energy. Then heat energy is going to produce a mechanical to rotational energy. So when your vehicle is running on the road, that is we are saying it is efficiency. Okay. In a similar way, when you are charging your EV and with some renewable energy source or any kind of energy source, then when it is moving on the road, how much of energy you are wasted and how much energy you utilize it to run your vehicle. So that will define your energy efficiency. So that energy efficiency is more in the electric vehicle compared to your IC engine. And one more advantage of the EVs is the sound pollution. So almost we can say the 99% of the noise we are reducing by using the IC engine, the motor which we are using in the BLDC motor or SMPS motor. So these motors will cause lots of reduce. So it will reduce lots of noise. So we don't have that much of noise when you are using this EV source. But recently the government also given some new guideline. So your vehicle need to produce some sound, because when you are driving inside the vehicle, so the people who is driving, they are sleeping. If they are not using any audio system or something, then they are about to sleep. So that's why they are making giving some guidelines to make some noise inside the vehicle. That is artificial vehicle sound. That is not for the which voice is noise is not coming from the engines. So these are the major advantages and disadvantages. So if you compare the efficiency of the vehicle, so this is Ford company they developed in the long back in 80s, which is called the well-to-wheel non-efficiency. There, so here let us assume so we are charging a electric vehicle and we are using the one conventional IC engine vehicle. This IC electric vehicle is charged by the one charger, which is power supply is coming from some diesel generator. So diesel also a byproduct of the crude oil, which is coming from the well. We are going to be crude oil separation we are doing. In similar way, you can use same diesel inside some well transportation system and send into some petrol pump, from petrol pump to our vehicle. So in each and every stage, so the amount of the energy is lost or the efficiency, if you are going to see the overall. So we are getting the 23% of overall efficiency from well to wheel when we are converting this entire energy into rotating energy on our road. Whereas in the IC engine, we are getting only the 13% of the energy efficiency. So I'm not going in detail. So how much of energy we are lost in each level and each component. So there is a concept is called the LONA, well-to-wheel internal vehicle architecture energy efficiency. That can be it will give more precisely. So each and every level. So when you are putting inside the petrol in the tank, then how the energy is going to converting, and each and every level, how much of energy we are losing. Those we can see inside these components also. But overall efficiency of the IC engine is 13 only, and the EVs are 23, which is almost more than double. So when you're comparing to the profitable or not, so how much how much we are paying for this IC engine and electric vehicle for the same distance. Here I given the one example for both the companies. So one is the EV Tata Punch petrol, another one is the Tata Punch, same company, same model, but it is a EV. So as company mentioning, so this is not Android. So we can, I took those only example from their website details. So which is mentioning your petrol vehicle will give the 20 kilometer per liter. Okay. And your EV charging 80 kilometers for 10 unit of charging. This is their claiming system, right? So both the cases, maybe in the petrol or diesel car, or maybe in the EV, there may be reduced, but overall, as we can take example. So the cost of the petrol, it is more than 110 now, but most of the companies, so as of we can understand, there is 90, 100 rupees if you're taking average value. So to run this 80 kilometer, so we require the 20 kilometer, we require the 400, right? So mileage is 20 kilometers for 100 rupees per liter. If you multiply, so divide with this 80 with the 20, then you get the 4. So the 4 liters of petrol we required, which is costing 400. So overall 400 rupees we required to travel by using the IC engine vehicle for 80 kilometer. Where you compare to the EV, so the on an average you can take 4 rupees per unit of cost for charging your battery. So for 10 units, it will take the 440 rupees. You can see there is 100 times. Here we are spending 400 rupees. There we are spending only the 40 rupees to travel for the 80 kilometer. So this much of on-road cost we are going to be reducing by using our EVs. So when point is coming to like, so for everything here we require the power. So how much of power we are generating and how much of power we are consuming inside. That is where the crucial role here. This is to get the some bit idea. I'm not going in detail. I'm going just to giving you overview. So in our India, so this is as per their Indian government website, Central Electricity Authority, as per 23. Central sector, state sector, and private sector. So overall installed generator capacity is 4,1760 megawatts of power supply. This is the installed capacity. This is like a different, like you can renewable energy, non-renewable energy, everything, including this much of power generating we have currently. So inside this one, so out of installed generation, we are overall generation nearly the 1,618 billion units we are generating. So, but our requirement is 1,512 billion units kilowatt hours we require the energy. The total energy supplied by this is 1,504 units kilowatt hours. So if you go for the per capita electricity consumption, that is 1,327 kilowatts of per capita energy we are going to be consuming. So our own consumption, so this is our own Indian consumption is 1,137 is a 1 billion kilowatt hours is our own consumption. Okay. And how much we are producing? We are producing the 1,386 billion kilowatts of power we are going to produce. And we are importing some of the energy also, that is 5.62 billion kilowatt of energy we are importing. And we are exporting. So we are importing from the small private sectors, and we are exporting to some small neighboring states or countries, or some private sectors also we are exporting to the 5.15 billion kilowatt of hours. If you go to the loan installed capacity for the non-renewable energy, it's a coal, lightning, gas, diesel, and total fossil fuel we are going to be generating in the 2,37,286 of megawatt. Out of the 100%, so we are generating 56.86% is installed from the fossil fuels. Okay. When you go to the renewable energy, we are installed is 1,79,332, which is a 43% of share. Right. Inside this one also, the renewable energy, hydro power station, wind, solar, and a combination. Right, waste to energy, small power plants, and nuclear power plants, including that everything, we are going to nearly approximately we are generating 43% of power from the renewable energy sources, which is non-fossil fuel. This is our energy, so generation and transmission and utilization from different sectors. So where we are in the global market. This is one old images. So this images almost it's proportionate, but the few details was changed. So as per 2024, this is a bit changed. But in 2020, if you can see, so we sold nearly the 1,19,500 units. Out of that, different states. So Uttar Pradesh, Bihar, they nearly took 26% and 10%. Delhi, Rajasthan, and so in the different sector, like a which company, Hero Electric, Okavena, Ampere, Aether, Revolt, some other companies. So different sectors. So before COVID, so our the unit sold in the electric vehicle segment is slowly is increasing up to the 2020. When the COVID was hit, then this is going to slightly down. But again, in the 2023, it is increasing. I think I included that graphs, but maybe you can see here. So in the same way, in the three-wheeler segment, you can three-wheeler cargo segment. This is for two-wheeler segment. This is for three-wheeler segment. So still 13-19 before the COVID, we are going to slowly, we are on the upward graph only for every year, 20, 31, 20%. But now after the COVID, we reduce it to nearly the 33% of we reduce it. Again, in the last financial year, we are nearly 40% of growth change is there. So it is going for some year-wise so registration in the EVs, only for EVs. It's all segment, two-wheeler, three-wheeler, four-wheeler, and heavy vehicles. You can see there is always in upward till 2019 and 2020 it was reduced. If you go to the global market, so in the global market, we are now still nearly only the 2 to 3% of the vehicles we are using inside in our India compared to the globally. But up to 2020, but 24, it's nearly the 14% of the vehicles we are going to use. So in out of that, so our share was Uttar Pradesh is still using the more electric vehicle compared to all other states. So there's a different types of segments are available inside the EVs. One is two-wheeler. We can say there's a two-wheeler vehicles. So e-rickshaw segment are the goods cargo segment for three-wheelers are the e-carts. And this is a small E5 goods vehicles also. And there is a four-wheeler segment. Sorry, this is not two-wheeler. It's a four-wheeler segment like a cars, SUVs, XUVs, different vehicles we have. And the bus segment, bus and the trucks and the small sports vehicles we are using for carts. So in the global market, so this is up to till 2020 and others. So this is a one small comparison where we can see the in different segments. So how many vehicles we are producing by the year wise. So it's approximately when we came to the 24th March, we sold nearly 21 lakhs, 2 lakhs 50, 2 lakh 20, sorry, 2 lakh 11,650. So 1 lakh 40,000 to within the only March 23 to March 24. This is the last financial year. We're almost done the double sales, our registration, the double sales from the RTO sites, if you can compare. And most of the vehicle segments, so in our India, we had the growth was in the two-wheeler and next three-wheeler and the goods. In the car segments also, we can see the lots of growth inside the two-wheelers and four-wheeler segment along with the two-wheeler segments. So which top companies are in the market, which is going to manufacture in these vehicles? So in the two-wheeler segments, if you go to the Hero MotoCorp, Honda Motorcycle, TVS Motor, Bajaj Auto. So these are these companies which is manufacturing both EVs as well as ICs. But when you see the sales in 24, so out of the overall sales, there is nearly the 1%, or what we can say that's a 0.9% of the electric vehicles they are started sold. When you go to the Honda motorcycle, so 2024 they didn't sold any motor vehicles, but in 25 the market they are also selling some electric vehicle. The shares they didn't disclose it, so I didn't mention that one. If you go to the TVS Motor, they in the 24 itself there is a nearly 10.5. I can say the 11% of their vehicles is already in a EV vehicles. Bajaj also sharing the nearly 10% of their vehicle. And some other companies like a Suzuki motorcycles or Royal Enfield. So these are still manufacturing the IC engines, but they will also, when the entire market will change, they will also going to convert in that IC engine to the electric vehicle. And the Ola electric vehicles. So this is well known for everyone. So Ola EV scooters or Ola scooties. That is 100%. They don't manufacturing any IC engine. They will only manufacture in the EVs. So that is 100%. So Indian Yamaha Motors also, they are only manufacturing the IC engines. Aether is also manufacturing only the EVs and the kinetic green energy and the power. This is one of the startup company. That is also started manufacturing only the EVs, which is also sold nearly the 4,000 in the March 24 alone. If you go to the three-wheeler segment, so there is a different companies and the percentage of shares I have already mentioned here. So Oga Marx's IT Clean Mobility, these are the two companies which only manufacturing the EVs in the three-wheeler segment. Where the other company like a Mahindra Last Mile Mobility, so it's a part of the Mahindra group, that is 92% of their vehicle is selling only the electric vehicles. If you go to the four-wheeler segment, so in the four-wheeler segment, Tata Motor, MG Motor, Mahindra, BYD, this is India, Hyundai Motors, BYD, BMW India, PC Automobile, Volvo, Mercedes, Kia Motors, others. So each and every company you can see there is a 30, nearly 40, 37, 2%, 20%, 114%. So the overall market, so 26% of the overall vehicles was sold in the four-wheeler segment in 24 was EV vehicles. Where in the heavy vehicles like a bus, trucks, this is also nearly 29% of the vehicles they are manufacturing in the EV segment. So this is a very good sign for the Indians and the industry. So there we are looking for the more opportunities and the works. Let's go to the overall internal components, how the EV will look internal side. Okay, if you look into the on the test bench or the powertrain system. So your front traction motor will be look like this, and your bidirectional charger, your charging point, this entirely charging station, and this is your battery. The different internal equipments are there. So we will see internal some more detail. Okay. So the major components in electric vehicle will be the electric traction motor, power electronic control. So this electric traction motor we will use to provide some rotational energy. So power electronic converter, which can be used to step up and step down and converting from AC to DC, and this all will be used here inside. Otherwise, the thermal cooling, it may be different types of cooling, air cooling, liquid cooling, or solid cooling. Based upon the vehicle and the requirement, they will provide the cooling systems. And we have an auxiliary battery. This auxiliary battery will use it for your auxiliary accessories, like your start, stop the vehicle, or for the GPS tracking, or for the system. Those purpose, you will use some auxiliary batteries. Another one is called the onboard charger. So onboard charger, offboard charger. We have two types of chargers in electric vehicle. So onboard charger means that when we are plugged into the charging port of the charger, we don't know whether it is AC or DC power supply. Let's suppose, but the batteries we require the DC power supply. Right? So in that scenario, if you are connected to the AC charger, so what they will do, the conversion from AC to DC according to the step down or step up, the power supply will be done by the charging system. Those system will be inside the car. If you are converting AC to DC and step up, if that is called the onboard charger. Outboard charger means so all the conversion process. So if it is a 3-phase or single phase AC supply, whatever it is, so that all will be converting into the DC according to the rating of the EVs, so which we are going to be using. So the charging pin will get the purely the DC power supply, that is called the outboard charger, because the charging system will be, everything will be outside. Otherwise, a traction battery pack. So this traction battery pack is our main battery. If you go some more in detail inside the vehicle, this is one of the plug-in electric vehicle battery. So I will tell you what is the mean by plug-in electric vehicle also. Plug-in means, so there is as I mentioned, there is a different types of vehicles where we are charging externally, and some vehicle by hybrid electric vehicle, we are not charging externally anything. We will use the internal energy source to charge our battery. I will show you in upcoming slides also. Let's see here. So from the grid, whatever the power supply we are getting, it may be the 3-phase, single phase or 2-phase. So this one is dividing into the 3 levels. One is called the level 1 charger, otherwise level 2 and level 3 charger. In the level 1 charger, we require the minimum 120 volts of the AC power supply. It is available inside the garages or offices. In India, we are using 240 volts or 230 volts of power supply systems. But if you go to the US, still they are using they have a 120 volts of AC power supply system. So that AC power supply also we can utilize to charge our vehicles. The first level. In the level 2, what we will do, it is required the single phase or 3-phase power supply, which is having a minimum of 240 volts of power supply, which can use as a public or private charging station. Otherwise called the, this is these two, this onboard, for single phase and the 120 volts and 240 volts, still we can do the onboard conversion. That means the whatever the charge conversion we required, that we can do the inside, the DC conversion of DC. But outboard charger, this is very commercial, like outside how we are using petrol bunk. In similar way, we have a charging station. There we will use the 3-phase AC or DC, the fast charging system. So due to this high capability, so the fast charging system require the more high level of components. The size of the components also going to be increasing, because when we are going to converting from 3-phase high energy into the DC, so their possibility of the generating more heat. So they require the good cooling system also, the conversion system. So everything is bit high level. So that's what we will do. Generally, this fast charging system, we will develop the outboard charger instead of onboard charger, because it will take much space inside your vehicle, and it is also harmful. And we need to take more precautions if we develop the fast charging onboard chargers. This is on the first level. We require the different type of chargers. So once we connected this AC supply, let this example I'm explaining here is the onboard charger. So when you're connecting the charger, so in onboard charger battery, what it will look like? So first it will convert the AC to DC. So in this AC to DC, we can use different types of converters. As in a power electronic background, people will know very well. So there you can convert different types of AC to DC power supply, which can convert. Then after converting the AC to DC, so there is a few ripples was there. We cannot generate 100% of pure DC. So in order to reduce those ripples, we'll use some power factor correction converters. So this PFC converter will remove the ripples, whichever is converted by this AC to DC converter. Then it remove the ripples and supply the pure DC. So here, after converting the DC, so as per this, whatever the voltage is there, we can step up or step down inside the converter itself. But the general structure is, after connecting pure DC, we will do step up or step down. So based upon our requirement, if we are taking like a, let us assume you are connected to the 2-level charger, but you require the only 120 or 240 or 50 volts of power supply for your 2-wheelers. In that case, what we need to do? This voltage we need to do step down. In some cases, like 4-wheeler, where we require the 440 volts battery, but you are only having a 240 volts of power supply. In that case, what we will do? We will use the one step up DC converter, which will boost your voltage from 240 to 440 or 880 volts. It depends upon the vehicles. So here from AC2, we are converted to the DC2 according to our voltage levels. Okay. So here we can do, after this one, converting in the DC bus. So whatever the DC bus inside traction system will be there, we are giving to this voltage. We'll use a one DC bus capacitor for the constant power supply, constant voltage. After this, so we have a one more bidirectional DC to DC converter. What this DC converter will do, it is acts as a buck boost converter. So suppose if you are using a single phase only and your supply source, even in the onboard charger, it can capable only up to do 120 volts or 220 volts, but your battery is still 440. So instead of developing here itself, what we will do one more step level up, and there we will convert this DC to DC according to your battery pack voltage levels. Suppose it's a 440 volt battery, you are able to converting 120 to 240, then 240 again is going to converting into the 440 volts to charge your battery pack. And why it is a bidirectional? Because when we require the power supply, maybe your battery or the motor which you are using, it may be required some step up or step down compared to your battery pack. You can do it. Another requirement is your auxiliary electric loads inside, like ACs, music systems, lights. So those things also required some auxiliary power supply. So what you'll do, instead of using the conventional lead acid battery, we can also use the lithium ion battery. So which can also charged by your HV pack. There is a high voltage battery pack will charge your 12 volt battery pack. To charge that one, we'll use some bidirectional converter. That power supply is given to the according to the step down based upon your motor and as well as your 12 volt battery or 24 volt battery. So here also we'll use one more DC-DC converter after step down. If it is required, we will do step down according to the motor. If not, we can also utilize this for to recharge your 12 volt or auxiliary batteries. And so as I mentioned, so BLDC motor or the PMS motor, this required 80 AC power supply. So the battery again is converting from DC to AC. And there we are converting this rotational energy into transmission system on the differential. So here the bidirectional work, how the bidirectional regenerative braking work. When this transmission system is rotating on the differential, so the motor will be rotating in this direction. Then that motor will going to converting some energy. That energy is going to utilize it to in the step back. This is also bidirectional. It can use it to charge your battery, as maybe 12 volt battery or maybe high voltage battery, according to your different structures of this one. Let's see some more detail, bit not in detail. Just give some briefly. If you go to the battery electric vehicle, so it will look like internal architecture, your battery, power converter, and motor. So your total energy supplied by the battery alone, where the power converter will be converting according to your motor. So whatever the motor supply rating is, it's so the India is a Nissan Leaf was the first electric vehicle, and still they are manufacturing in the same architecture. When you go to the hybrid electric vehicle, as I mentioned, there is a different types of hybrid electric vehicle. One is series hybrid electric vehicle, parallel hybrid electric vehicle, and series and parallel hybrid electric vehicle. So inside this also, the traction motor is used for the propulsion of the wheel, but the battery is used as a fuel energy sources. So both we have here, right? So the IC engine is connected to the motor here. It's a parallel. Sorry. So in the mild hybrid electric vehicle, what happened? The mild electric vehicle, so the battery size will be bit less. It is maybe 12 volts or 24 volts or 48 volts. We are not going to using for the high voltage battery here. Here the main source for the power supply for your motor traction is IC engine only. It is a only supporting role here. So where we can save some fuel and to increase the efficiency. Like example, so here the Monda Jazz hybrid, these are using for the mild hybrid vehicle. So plug-in hybrid electric vehicle, what they will do? Here the construction will be same. You have a IC engine and you have a generator, motor system, and power converter. But the changes here, the battery size will be a bit more increased, and we can able to charge from the external. So plug-in hybrid means so the plug will be there to charge your battery. So external power supply will be used to charge your battery. Like we have an example of Toyota Price inside the market. So these vehicles we can divide into the, as I mentioned, series and parallel. The previous one was the series and parallel. So CB hybrid vehicle, if we take, so all the system is connected inside in the vehicle architecture is in series. So you have fuel cell, you have IC engine, the IC engine is connected to generator, and generator is connected to the power converter, and power converter is connected to the motor controller to motor. And the battery power supply we are getting from the power converter to here. So entire power supply we are getting to the motor after the power conversion system. Where the IC engine act as a generator, here it's also act as a generator for this overall power converter. So whatever the energy required, we are generating from here. Whereas in the parallel hybrid vehicle, what happens? So as in the starting slide, we saw that, right? So battery and as well as for the fuel tank, both are available in the parallel. They're connected to the one differential transmission system. To propel the vehicle and the motor is a IC engine coupled with the same shaft system. The other architecture is a series and parallel hybrid vehicle. So here both the structures, like we can get the high energy torque as well as for the energy saving. Both the systems we can use. So where we require the high torque, in that scenario, we will use the series hybrid vehicle. Where we require the energy power supply savings. So sorry. So there, where we require the save the more power energy, we will use the parallel hybrid system. Where we require the high torque, we can use the series parallel. So vice versa, both the complexity architecture also we can develop. But as the complexity will develop, the control algorithms and the controlling technology is required more space and the more knowledge. So it is increasing the cost. Overall cost will increase, then it's going to impacting your sales of the vehicles. So there is a few vehicles also there which going to provide both the series and as well as a parallel architecture and both the advantages like a high torque and the power saving conversion system. Like Honda Civic, Honda Sonata, these are the some few markets available vehicles which can be provided this one. So as you saw that, so why we require the electric vehicle batteries, what is the need of electric vehicle? What is the comparison between the IC engine and the vehicles? And we also saw that how much of more energy we can save or cost we can save. And we also saw that so how much of what kind of architectures we have, what is the internal architecture, basic architecture inside the vehicle, how we are converting some AC to charge the batteries. Okay, let me go to the batteries. So somewhat in details inside the battery. So how you select the battery? So when you are selecting any battery for your vehicle, so what are the major parameters you need to look into that. Apart from there is some more things are also there, but we are not going in detail that much, but we are dividing into the different categories like electrical requirement, temperature, humidity requirement, charge condition, life cycle, and dimensions and other. So I will give you more everything. So whichever we need to, when you are selecting any cell, these are the things you need to must and should need to be considered. The first one electrical requirement is voltage requirement. That is how much of maximum voltage and how much of minimum voltage your cell or battery is capable. That we need to must and should take. Why? Because this rechargeable battery is having a limitation. Once you will discharge completely or less than its minimum voltage, you cannot recharge again. It's called the dead cell. Okay, or you can see in your mobile phones, once after 1 year or 2 years or maybe 3 years, your battery will charge within a fraction of seconds, like 5 minutes in from 0 to 100%. Where normally it take 1 hour or 45 minutes, no, it will charge within 5 minutes and discharge also within 5 minutes because it's all limited capability also reduced. At that time, it cannot hold those voltages, energies. So due to that, so we need to check that what is your maximum and minimum voltage is capable. According to that, you need to select the number of cells. So the when we are manufacturing the battery in our company also, first thing is we will look into that what was the space given to you inside the vehicle, like the dimensions of the vehicle. So for 12-volt battery, so where our current product is working, so we have a limited space. We cannot use entire vehicle or some specifically. So other component, every team, they are giving their specifications and their space according to their space. Suppose we have a 1 feet by 1 feet, so 1 into 1 feet of the spaces only they are given. So according and the capabilities 12-volt battery you need to provide, and the rating also we need to define. Like our battery is 40 Ah battery, which is 12 volt. So 12 volts for 40 Ah battery to develop. So how how many cells we require, that we need to check. So each cell voltage also it's playing a major role. And second one is the continuous load. That means so for 40 Ah battery, you can assume that how much a maximum and average or minimum current you can capable to produce. Okay, so most of the cells, their capabilities they are mentioning in the milliampere. Okay, not directly in the ampere. And you can also see the intermittent load. Intermittent load is nothing but when you are doing some charging or discharging or turn on, turn off the vehicles. There we require the pulse, immediate spike of the current, like 1500 or 1200 kind of amperes of current we require to start the vehicles. So during that time, so how much of intermittent load you can able your battery to battery is capable to produce. That is also you require. So on off condition, this is called the life cycle. So how many times you can turn on and turn off? Well, during turn on, turn off, are you identifying any kind of issues? Second one is temperature and humidity. So why it's playing a easier role? So as you know that, so different companies, we are importing the vehicles also from the various countries also, and we are also exporting to the some country. So all different countries have a different atmosphere. If you go to the Dubai, that area, the temperature is always more than 40 or 30. So there is a humidity is very high and the temperature is also very high. If you go to the North America side or European countries side, their temperature, maximum temperature, they can see the 15 or 20 degrees. They won't go beyond that one. So in that scenario, we need to look into that, the temperature, humidity as your cell is capable or not. Excuse me. Someone can mute it, please. Yeah, thank you.
Sir, we have muted, sir. Unfortunately, it has been
Okay.
started.
Yeah. Thank you. No. And regarding to the temperature, the storage temperature and humidity, this is also playing a major role, because when you can also observe, if you are not using your vehicles for long duration, your battery is going to be discharged completely. So in that scenario, what you need to do? So how much of time you can able to store your batteries? When we have done some battery selection for our vehicles, which we are working in currently. So there we found that when when this batteries was transported from other country to one more other different places, so the batteries was completely discharged because the reason was the capability of their battery storage is very less. So by the time the temperature and humidity which they were mentioned, so according to that, it was not working there. Once you fix it in the vehicle, the battery was fully discharged. We are unable to use this battery. So that's why this is also storage temperature and humidity also you need to be tweaked. For this each and every component, then every cell manufacturer and the companies will do the testing. They will do different kinds of testing, bench testing, hill testing, seal testing, and the overall battery pack testing also. Okay. The charging time. So how much of charging time is taken to charge from 0 to 100%? So whether it is a full charge, it's having a fast charging capabilities are there or not, you need to look into that. And what is the minimum charging temperature is going to be generating during the charging. So when you are charging from one cycle from the initial battery, so your new battery will produce less amount of heat. If you are example, if you take your mobile phone, when there is you buy a new mobile phone, you are charging, you will not feel any kind of heat inside your phone or battery side. But once the phone is getting old, like after 1 year or 2 years, if you are charging your battery, you will find some heat. Maybe due to some thermal system, we can able to cool it. But as the time goes, what happens? This temperature is going to be increasing, right? So you need to look into that while charging, how much of temperature your cells are producing. This is also important because this is also one of the factor while you are selecting your battery cells. There, what is the minimum and maximum charging you need to keep your cells are producing. Due to this, it's going to impact on your thermal management system inside your battery. So that is going to play a major role. Other one is life factor. So here the life factor is nothing but a life cycle, so number of cycles. So here one cycle is nothing but charging from 0 to 100 and again discharging from 100 to 0. This is called one cycle. So how much cycles your battery is capable? So there is some 5,000, 7,000, 8,000 cycles per their cells. So according to your requirement, you need to be selected. And the storage period. So without using your batteries, how much time you can able to store it? That is also they will mention. I will show you the one example sheet also. So how they will mention the details. In the starting I mentioned, so in every vehicle we have based on the vehicle dimensions architecture, you need to select your battery size. So this height, weight, length, width, mass, and terminal shape, this is play the major role, which will decide the size of your battery. So other factors also there. It's not. I'm not going in detail depth, but this is also you need to must and should look into that when you're selecting your cells. Like atmospheric pressure. Why this atmospheric pressure is important? Because in the different places when you are going, the temperature of atmosphere will be increasing or decrease. In the cold countries, if you go, the atmospheric pressure is a bit high in the night time. And the very high temperature also is going to facing some high atmosphere pressure. This pressure plays on the terminals of the battery is a crucial role. It may be sometimes it may be going to be damaging bitterly. The health of the battery is going to impact it. And the mechanical condition. So whether you have a different batteries, so you have a cell type, pouch type, cylindrical type, different material you are using for this mechanical, to manufacture this vehicle. So you need to look into the what is the mechanical condition, whether it's mechanically withstand with the according to our requirement or not. And the safety level. So there is a different types of safety levels, ISPICE levels, level 1, level 3. Different companies having different level of safeties, they will do testing. So which kind of testing standards they have followed, whether it's as per your requirement or not. Interchangeability. So that means let us assume you are manufacturing a one big 80 kilowatts of battery. So what we required in yearly required, assume there is 100 cells we require, 200 cells we require. So out of 100 cells, if some cell was having some issue and it was damaged, so it is there should be a possibility you need to be interchangeable. So we need to be replaceability should be available. It should be replaceable batteries. You can use that kind of batteries only. Some batteries will come like if one cell was damaged, so we cannot replace it. Right? It is a completely interlinked to each other. So that is unitary. So the marketability is nothing but it is like it need to be available in the market. Today you are manufacturing your vehicles, and after 5 years you have found that this cell company is not at all available in the market. They closed it. Then whatever the vehicles you sold to the customers, they will ask you to replace the battery. At that time, according to your vehicle dimensions, available batteries, so the batteries will not available in market. Then it's going to be a big issue for you. So for any vehicle, whichever select you are selecting, that need to be available inside the market for the long duration. You need to look into that. And the price also need to be according to your requirement. I'm not going in depth. So you know that there is two types of batteries. The primary batteries, you also know that we are using in several remotes or in watches, which is only non-rechargeable. It's come with 100% charging. We can only utilize it, and once it's going to 100% discharger, we cannot use it back. So if you go internal terminals, so positive terminal and negative terminals, we have a carbon rods or cathode mix, different types of electrolytes we will use inside this one. And the zinc consumed cascade we will use, and zinc cans we will use. So this is different chemicals will come. It's not a single chemical, but the primary batteries we come with the full charge. We are recharging and replacing the batteries. Where the rechargeable secondary batteries are the rechargeable batteries, which is like a one anode and cathode will be there, which is be separated by the electrolyte, right? So from through the electrolyte, when you're charging or discharging, your electrons is moving from the anode to cathode and cathode to anode, based upon charging and discharging. And this is also limited. So as I mentioned, so every battery having their life cycle. So we can use 5,000 or 6,000 times. Then during that time, the capability of the electrolyte or cathode anode materials is going to be reducing. The capacity of the battery is going to be slowly reducing. So the Ryzen plant which can define your power energy density. So the power energy density is nothing but so with less space, how much of high energy you can save it, right? So in market, we have four types of renewable energy batteries are available. We can say the fuel cell, which power density is less because the energy density is high. So it can be able to provide more power, but we require the more space. So size of the fuel cell, we require more space to provide this much of energy. Other one is the lithium ion batteries or lithium nickel metal hybrid batteries or lead acid batteries. So this having capability of the much power, more power density, but energy density is bit less compared to this one. So like lithium ion capacitor, so which is coming more high power density. So which can, in the small size, we can store the more energy. There is one small comparison I have given for the different kinds of lithium rechargeable batteries, right? So energy density point of view, as I mentioned, so watt-hour per kilogram, so internal resistance, life cycle, fast charging time. So overcharge tolerance is nothing but when you are charging your battery. Let us assume your battery is a 4 volts battery, and when you're charging it, the voltage or the current is going to be more high, right? Due to your charging problem or due to your connector problem, something will be there. So how much of it can capable to tolerate it? Right? High power it can be able to tolerate, or if just because of 1.1 volt or the 2 milliampere, 5 milliamperes of current increases, then immediately it's damaging or not. That is called the overcharge tolerance value. And self-discharge per month. So at the room temperature, I think, but at 25 degrees centigrade, how much it's discharging itself without utilizing. Okay. And the cell voltage. So nominal cell voltage, each cell chemical manufacture cells, different chemical composition. So how much of its nominal voltage are available, and the load current. So what is the peak current they can able to provide, and what is the best result they can able to provide. There is about the 2C or 1C is here I have indicated. That's nothing but 1C is nothing but let us assume your cell is a 200 mAh battery. I'm just giving 200 mAh. If we are charging with 200 milli current, that is a 1C. If you are charging with 400 milliampere, that is called by the you're charging the battery with the 2C. In the similar case for discharging, if you are having a 1 ampere battery, if you're discharging with 1 ampere to the loads, then it is a 1C. If you're discharging with 10 ampere to the load, that is a 10C. So operating temperature. So as I mentioned, if different conditions, we have different temperatures based upon the different countries. So which cell having how much of capability and the maintenance required. So when there's a rechargeable battery, so every battery is very required some minimum maintenance to clean that dust or it's forming some solid white solids on your terminals. So those kind of basic things we require to do the maintenance. So typical charges in the market availability. So cost per cycle, there is nothing but one charge and discharge full cycle. So when this was available inside the market and what is the impact of this due to this chemicals on the environment. So the highlighted one I mentioned, this is the best one in this each category. If you go to the energy density point of view, the lithium ion battery is having a 110 to the 160 watt-hour kilograms having energy density, where the internal resistance, if you compare, the internal resistance is bit high. But for the 12 volt lead acid battery, this is all for the 12 volt battery pack segment point of view. I'm saying it's a less than 200 milliohms inside the lead acid battery. When the resistance is increasing, the capability of the power delivery is going to be reducing. So that's why always need to be the less internal resistance and high energy density. Then you can able to deliver the more power with the small size. So if you go to the life cycle, so nickel cadmium battery is having a high life cycle compared to the all others, which can be up to the 1000 or the 50, 500, 300. Where the fast charging, so it required, so based upon the same capability cells, it's required only 1 hour, whereas the other cells will take 2 hours, 3 hours, or 8 hours. Lead acid will take the 16 to 8 hours. This is the tolerance I mentioned. So lead acid battery is having a high tolerance compared to the all other. And the self discharging is also the lead acid batteries will sustain for a more long time. But the nominal voltage is the lithium ion batteries having a high nominal voltage compared to other batteries. When there is a nominal voltage is less, that means the more number of cells are required for the batteries. So as the number of cells increases, the cost is increasing. Where is a peak current? So the nickel cadmium batteries can able to deliver up to the 20 C charging and discharge, where the other batteries can able to deliver for the best performance. It's not for the every time. For the best performance, they can able to up to go for the 5 C. And the temperature, the operating temperature also, nickel cadmium can operate up to the -42 plus 60. Where the lead acid battery lithium ion which can able to operate up to -20 to 60. The maintenance also, from the maintenance point of view, lithium batteries are lithium polymer batteries which not require the regular maintenance, where the other batteries were required with maintenance from the 2 months or 3 months or 6 months. The cost point of view, the lead acid battery is having a more very cheap compared to the all others. For the cost per cycle, we can compare. This is a $0.04. So we can say it is a 2 or 2 rupees, 2 or 4 rupees for Indian rupees. You can. So from 1950 it was using. So, but nickel cadmium and nickel metal hybrids, they are going to be banned in overall world due to this chemical reaction. So most of the batteries we are using lead acids and then lithium ion lithium polymer batteries in the market currently. These all batteries are having a high impact or the moderate impact on the environment. So there is a future battery. So apart from this one, so the development on the battery side will be the future lithium batteries. So if a lithium sulfide or lithium, there is some more chemical composite is coming for the anode and cathode material, which is going to be increasing its capability from 300 to 400 kilo. Sorry, the cost is going to increase in some. It's approximately some 400 watt-hour kgs with the same size of battery we can get from the lithium future batteries. But the cost also we are going to reducing from almost half of the cost. We'll get the double size capability batteries. Zinc-air batteries also another one research area. Where the lithium sulfur batteries and lithium air batteries also going to be under research. These all are under research and development. This no company will using currently. But when this battery will come into the market, the energy capability, so the size of the battery is going to be reduced further, and the capability, like if your car is giving for full charge 400 or 500 kilometers of mileage, no, it is going to be like 1,000 or 2,000 kilometers per charge. So we need to look into the what happened because of this C rating. So there is this C rating is we are using for two types of cell. One is for power cell, another for the energy cell. The power cell is nothing but which can able to deliver the maximum power with less time. Like if you go to the racing cars where we require the more power within less time. So in that scenario, what we will do, use the power cell which can able to deliver the more power, like a 5C, 10C ratings of power supply. Where the energy cells is nothing but which can deliver the less amount of power, but it can deliver for the much time. Like if you require we don't require within 5 seconds like 100 kilometers per hour speed, right? In our Indian roads or any other country roads, we don't require within that less time. We require the more energy to travel for a long distance. In that scenario, we can go for the energy cells, which can able to deliver the more power with more time. If you see the data sheet of the any company cells, so it will look like this. If you are not aware about the data sheet, if you are already aware of the data sheet, so you need to check. They will provide the details like this for the cells. So which kind of technology they are using, what is the nominal capacity, what is the minimum maximum capacity. Well, they will also mention what is the recommended charging was there, what is the energy density and the charging continuous. So how much of what is a continuous charging like AC power supply, like continuous DC you can use for the 2C rating. It's a 44Ah battery, so you can use up to the 88Ah charger for this battery. For discharge, you can do the 3 times of this can able to discharge it. For the pulse it means continuous stop, down, stop, up, like that kind of things. We can go for the stop. This is 4CR up to 10CR. The life cycles and the operate temperature, dimensions, weight, everything they will mention here. Let's go to the types of batteries, how they will make the battery. So yeah, we have a less time, so I will go a bit more fast. If you have any doubts, you can please raise your hand. You can ask the question also. There is a 4 types of cells inside the market. One is a button cell, which maybe you already know that it's available for our cell, hand watches we will use generally. In EVs, we will use these 3 types of cells. So one is called the cylindrical cell, where it's the material will be same, anode, cathode, and the separator positive terminal, as I shown in the primary secondary battery comparison. Here also there is same thing. So positive, negative will be there, one separator will be there. But only the construction, the mechanical construction will be going to be changing. Here they will mold into the cylindrical format. They will do in the prismatic. There is some hard solid type of case. You can observe this one inside your mobile phones. Okay. Other one is called the pouch type. So it's compared to the prismatic manufacturer. This having a more thinner. The material will be same, but only the mechanical, the outside, the construction will be different. So this entire cell, so what they will do according to our requirement, they will connect to each other. Let us assume these are individual cells. Actually, it's a modules, but it's let us assume each and every module also they have a multiple cells. They will connect to series and parallel according to voltage and current requirement. Then number of modules they are going to connect to again series and parallel to make your overall battery pack. In this way, we are going to convert it from cell level to the battery. So when you go to the inside, and you see inside the traction battery. So if you look into that, so house of the upper shell one will upper shell with there, which is going to protecting your battery from the all kind of atmosphere or mechanical everything. And the below also you have a one more coolant distribution tank. So this with these pipes we are going to be sending inside the coolant and hot air is coming outside. So engine everything gasket. Though one more lower case will be there, which is going to mount all these pipes. The cell modules, like as I mentioned, so all the cells we are going to bring inside, and your charging pipe or upper level coolant pipe or HV connectors, HV also. So whatever the power supply is coming inside and we are taking from the outside. So everything will look like this. It's not a for overall it will look like this, but internal parts will be multiple parts are there. These are some top companies which is going to manufacturing the cells in different countries, and these are the countries which manufacturing the capacity of the cells in the worldwide. Let's go to the much more details for the battery management, how this battery management will work. So the main function of the battery management system is to protect the battery from the different kinds of issues like over voltage, over current, over temperature, or any mechanical damage will be there. So it need to be only protection as well as to indicate to the customer, right? So if there is a over voltage happen, so voltage was very high. So the customer know that, or the service person know that how much of voltage, which one is caused that issue, your battery was fit. This everything will be done by your battery management system. It like a providing the window for you to how to what are the operations happen, what was the damage happen, which production was failed. So due to that, what is your battery capability, what is your health of the battery currently. So this everything will be done by the battery management system. So the major thing is it will measure your voltage, current, and temperature using these 3 parameters. They will do the SOC estimation, your battery health estimation, and they will keep your batteries in the cell balancing system. This balancing system also very crucial because to maintain that, by maintaining the cell balancing, we can avoid the overcharging or over discharging of the cells. So all the cells are keeping at same level, then our battery pack will be sustained for long time. And it will also, by measuring this parameter, you can also provide some power computation limit. That is nothing but at how much a battery is capable to deliver this capability. and when you need to replace it. Those things also it can help provide. This everything is called the safe operating. So how many types of failure can be caused inside your battery, to which can protect by your BMS? One is just like failure, like a short circuiting due to any wire or short circuiting, or maybe the physical damage is nail penetration, or maybe the cell will be completely over discharged, or maybe there's any heat due to the firing or anything happen. This any kind of causes when cause your failure of your cells. So when the one cell will fail, what it will do, it will going to be propagate to the all our cells. It's going to impacting nearby cells as right. Then once the one module is going to impact, then overall battery pack is going to be impacted. So one cell will cause the entire battery pack failure. So what are the failures may cause? Overcharging, short circuiting, dehydrate, penetration, overheating, or external short circuit, anything. So this all will cause us from internally or external failures can cause the various kinds of issues in your battery. So this all we can prevented by using the battery management system. So if you look into the any battery management system, it will look like this. So one is for the first one is used for the communication. This communication system is between communicating between the various functions, like your OEM, like when the customer is driving the car, so it need to be indicating like, okay, your temperature is bit high or your temperature is low, your battery charging is high or low, you need to be charged. So everything we are getting information through this communication. We have a temperature, current and voltage sensor. So this will be measure the various parameters of your batteries like voltage, current and temperatures. And your SOC estimation, like it is like internally you have to develop some algorithm which can be indicating your state of charge, state of health, and your thermal management when there is a temperature is increasing or decreasing. You have different thermal sensor which can be a temperature sensor, which can indicate what is the temperature currently and how much of coolant you need to be let into the inside the battery to prevent any thermal hazard. That will be done by the thermal management system. Power optimization is nothing but there is a different when you are using a different algorithm, so it will also consuming some power inside it, or it can able to deliver how much of power you can able to deliver it. So those everything, all the functions will be optimized by using some power optimization control algorithm, which can also be we can install inside your batteries. There is some displays. And this there is some few features as I mentioned. There is a self-supervisory control system. Sorry, can you please mute yourself, someone? Yes, someone raised a high hand, please. You have any question? Kiran Kumar?
No, sir. Please continue, sir.
Yeah.
Is by mistake it has been happening. I think.
Okay. Yeah.
Okay, sir.
Till we have 2:30, 3:30 only, right?
Yes, sir. Up
Yeah,
to 3:30.
Yeah, sorry, I took much time. Okay, we'll go bit more brief. So as I mentioned, so cell supervisory, which can measure, monitoring and control the supervisory control system. There is estimation system. So this is going to be estimating your state of charge, so how much of battery capability is left, state of health, when you need to replace the battery, state of power, how much of power capability is left, state of energy, how much of energy it can able to deliver in the next few seconds or next second, depends on algorithm. And cell balancing. So to do the cell balancing, we need to keep always, as I mentioned, so not to avoid the overcharging, over discharging, we need to do cell balancing. That can also done by the BMS system. So fault handling, like fault detection, fault isolation. If there is any short circuit happen for one cell, it need to be isolated from the all other batteries, other cells. And warning and safety system, as I mentioned, so different safety systems we need to do it. We require to protect this one. And thermal management and the communication system, we will use the CAN or any standard internal protocol systems we will use. And dehydrating capability, so reducing the threshold values and loading limits in the face of any faults happening. and scalable to the hardware, like a step up or step down to the size of the battery. Based upon that, we need to do it. And the low power consumption, or the minimum, how much of power we are consuming by itself, there is a more high capabilities of the batteries. Okay, so if you look into the real hardware, so there is a 3 major component which play these details. So analog front-end communication. So this analog front-end, what it will do, it will collect the information analogically, like temperature, voltage, current from the sensors, and it will be converting into the digital form to give your microcontroller to do the estimation parameters. So BMS having a main microcontroller. This is a latter, like this is one main microcontroller. The analog front-end will be there. This analog front-end will get the information from the sensors and the communication interference, which will go into communicating between the various factors. 1 minute, guys, excuse me. Sorry, guys, I got one call. Yeah. So the AFE, as I mentioned, so cell monitoring, the balancing, and local control and safety functions, this all will be done by because of the information we are getting from the AFE. If you go to the inside the BMS, it will be dividing into the 3 in this way. So you have an onboard charger, or your motor control, or motor control ECU, or motor ECU communicating through the CAN communication system. This information we are getting from the, they will pass from the thermal management system, or temperature sensor, or speed, or the coolant flow. This will be controlling on another level. On the inside, so whatever the state of your master controller or BMS will be do, that will be going to estimate your state of charge, state of health, and state of power. This communicating between the external devices. So how much of state of charge, state of health will be is there, that will be communicating through the your CAN communication. So inside the BMS also, there is a different types of architecture. So there is slave BMS and master BMS. Centralized, decentralized BMS systems will be there. I will show in upcoming slide. So there we will get the this is your AFE, like input charging, cycling, or analog input, analog current, voltage that we are measuring here. Here from the your slave BMS, you'll get the information that is going to your master BMS. Again, master BMS will be the instruction according to your algorithm, and it will going to be controlled and the monitor by your cells or the battery packs. With that, we will estimate these parameters. If you go to the architecture of the battery management systems, it will look like this. So your the red line, whichever is mentioned, this is a high voltage DCs. The high voltage AC lines also will be there, which is going to use it to charge your batteries, and the 12 volts are the low voltage batteries, which is going to use it for the your communication purpose, and the CAN communication is indicating with this purple lines. And the analog sensor values is also will be there. If you go to this charging port, we are going to charging, which is going to onboard charger. There we are going to the power distribution unit. Inside the power distribution unit, before entering into the battery pack, it is going to protecting your power supply battery from the power supplies, external chargers, like main contactor, high voltage sensor, isolated monitor, and current sensor. This all will measure, and it will be estimate and giving to your master controller. Okay, this much of power supply we are getting. This is according to our requirement or not. If it is not there, it will be rejected, or it will say that okay, the over voltage or over temperature or over current will be there. You are unable to charge your battery. If everything is fine and your BMS, master BMS is approving it through the communication, well, then your power supply is going to your battery pack. So there is a number of battery internal slaves and battery modules will be there, which is going to charge. Once the battery is charged and you remove your charger, then again it's going back to the power distribution unit, to the DC-DC converter. So before going to apply to the power supply, we will go into step up or step down to the DC-DC controller or motor controller. There we'll use for the auxiliary battery or the motor. So this all AC software is we will install inside your master BMS system. If you go to some more internal details, so it will look like this. Your HV battery will be there. Here we have a battery thermal management system, which can allow you to flow the 12 liquid coolant. Through the thermistor, we will sense the temperature. Based on that, we will take the action. The master controller will take the action and will allow the coolant flow. In a similar way, there is from HP battery, there is a emergency switch will be there, which emergency switch which can use it to control your power supply through the battery or the load to the power battery. There is one charging socket. So as I mentioned everything, so it will some more bit detail. There you can see that your HP internal systems. As I mentioned, this is all the functionality of the microcontroller, which can be estimate, external communication will control, and the power distribution will also be controlled. Overall system coordination will be done by your microcontroller. And there is a different kinds of communication systems for the AFE. There is a mainly ISO, internal system protocols, and CAN bus are the wireless, different kinds of communication system they will use. So this is a BMS main controller. So this analog front end. So there's a one small example I have given. You can also search for the AFE ISL 7016. These are different models. So if you can search it, you will get some more details about these controllers. We're out of time, so I'm just skipping few slides. So there is a different types of SOC estimation algorithm, like a direct method, bookkeeping method, adaptive method, hybrid method. The Coulomb counting, most of the companies they are still using because it is by measuring the current directly, we can able to estimate it. But there is a few disadvantages also. This accuracy is not 100%. There is a few losses is there while computing the Coulomb counting method. Where the adaptive methods are used, this method is nothing but by using the current value, you can estimate the next value. So in this way, we can estimate, we can increase the efficiency or accuracy of this estimation by using more. So by combining both the bookkeeping method as well as the adaptive method, they have some more method is Kalman methods or any other neural network fuzzy methods, which is a hybrid method, which is providing both the advantages. So these are some basic formula how to calculate the SOH of the battery. So SOH of the battery is nothing but the health of the battery. So present capacity and the beginning of the battery, how much of your capacity. Yes, by using these two parameters, you can able to find out your battery capacity, battery health. So SOH also we can able to estimate in the different methods, direct method, model-based method, adaptive methods. That's all we can do it. So state of power that can release observe how much of battery your power battery is capable in the next time interval. That also we can estimate by using different methods. So power integral method, equivalent circuit method, data-driven methods. We can use this one. So this basic formula to calculate the state of energy is remaining energy inside the battery and the maximum energy you can able to deliver the battery at the full charge. So that will define your state of energy. The cell balancing, we have different methods are there. So passive balancing and active balancing. In the active balancing, what we will do, whichever the having highest, that will transfer into the lowest cells by using a single cell to cell or one cell to all cells. Whereas the passive balancing, what we will do, whichever having a high voltages, that we are discharging to the whichever having a minimum voltages. This we can do in a two way, one during a charging, other one is during a discharge. So each method having one advantage, disadvantages. If you go to the passive balancing there, by using the some switcher resistor, what we will do, we will transferring that energy in the form of heat. So we are wasting energy there. Where in the active balancing, we are transferring to the energy to the other cell. So there we are utilizing that energy, but to utilize that converter system, we required some converters, switches that is going to increasing, and the complexity of algorithm also we require. There's a different types of methods are there to do the cell balancing topologies by using switch resistors, fixed resistor, capacitor based, inductor based, or converter based. So this different, each one is a one research area we can assume to do this area. A small example I have given where we are using a fixed resistor when there is a one cell was imbalanced. So your controller will say that, okay, this cell was having a low voltage compared to this two, then this C2 and C3 will close until it is going to be equal to this three, this first one. Then all the switch will be open. And similarly, for a switch resistor, so any one switch, let us this was the unbalanced, and then according to the cell consumption, so it will also going to balance. But here is a fixed ratio, only one switch. Here we'll use the MOSFET type. So multiple switches will be there, we can convert. Other one is the active balancing, so where you'll use the capacitor or some converters in between the cells. So whichever having IS, that energy we are transferring to the capacitor or converter to the other cells to make the balancing. There is also converter based, so in between the cells we'll use some converter, step buck converter, bush converter, buck bush converter, or the cuck converter to do the cell balancing. So this is a cell lithium failure model analysis. We can say the FFA analysis or failure model analysis. There we will define the what is the problem, what is the consequence, when this consequence happen, what is the action you need to take, what is the final result. Example, here the cathode was breakdown. So when the cathode was breakdown inside the battery, it will release the oxygen. That oxygen will increase then pressure inside the watt. So when the oxygen increasing, it may possibility is a thermal runaway. So what you need to do, you need to release your pressure valves open. Then your pressure will release. So in this way, by doing the failure mode analysis, we can prevent any kind of problems inside the battery. to do this, each and every requirement which you are doing during a battery manufacturing, you have to segregate all problems and what are the consequences. When these consequences happen, what are the actions you need to take? This is called the functional failure analysis also. So we need to do the protection from the battery from different way. So over voltage, over current, under voltage, under current. Different methods we can use by using these methods. So optimization power, as I already explained some details. So the future, so BMS will be called the BMS digital tin system. So there we will create the battery by using the battery data with the some simulators. We will get all the data, and we will develop the digital twin batteries. So which can where we can use our entire algorithms to do the more efficient way to utilize the battery instead of directly using method. And the thermal management, so the each and every cells, as I mentioned, so it having some specific temperature, they will provide the optimal energy. If you go to the lithium-ion cells, it can provide the maximum efficiency between the 15 to 45 degrees centigrade. If you are reducing the temperature also, the dynamics will be placing on forming on your cell terminals, so it is reducing its capability. If you are increasing, it's going to melting down and its capability will reduce. That is also increasing your capability. So based upon the according to cell temperature, operating temperature, you need to maintain that. Each cell having a different operating temperature, but this is optimal temperature of the most of the companies manufacturing cells. So thermal management is also playing very important role. So I'm not going in detail. We are already over time for 5 minutes. So there is a liquid coolant systems are open based upon the your capacity and the battery life will be increasing as per your temperature increasing or decreasing. I have given small example here. So there are different methods we can use for the cooling also. Power consumption, heating method, contact between the coolant based upon that direct cool, liquid cooling, air cooling. So these are the, as I mentioned, there is a different types of topologies in the battery management system. One is called centralized BMS system, where all the cells are connected to the one central BMS system. Another one is called the module type. So each module, there is a master and the slave module will be there and a master will be there. So this between modules are controlled by this master. And second is a master and slave. So there is a multiple slaves are there per few cells or 2, 3. Here the 3 cells, 1 slave is there. Here also 3 cells, 1 slave is there. This slave will get the information from these cells and it's passed into the master controller. And the master controller will define the based upon this data, they will take the action and provide the information to the slave. And slaves will take the action on the side of the cells. Other one is the distribution method. So in the distribution method, each cell having each BMS controller, and this all connected to the one centralized cell or master. If you do see some more details, so it will look like this. So central master control unit will be, so all central control unit connected to the directly AAP to the each cell we placing on each and every cell is connected. So when we are connecting some hundreds of cells to the one controller, it is going to be very complicated. So it is very difficult to manage, and if any fault will happen, it's going to taking action. So action taking is easy, but the controlling and the communication is very difficult for this kind of system. In the modular type, so master controller will get the information from the slaves and slaves will be going to control in the some bunch of cells. The distributed, so each and every one master controller will be there and each and every cell there is a one slave will be placed. So it is a very easy control and very efficient, but the cost of the due to this number of slaves is going to increase in the cost is also going to be very increased. So there is a different types of opportunities in the different fields. So I have given few companies which is going to offering. So the on the hardware side, testing side, engineering side, system engineering models. So these are some companies. There are a few references which I took. So if you have any questions, so please unmute yourself. You can ask your questions, or you can maybe chat, send your chat. If there is no questions, then over to you, Kasim.
Yes, sir. Thank you, sir. Thank you for the wonderful session. We request participants to please interact with our resource person. So, as it is a very booming topic, latest trendy topic, and also from the industry, he is from industry. Please make utilize the opportunity. So participants are requested to interact. Dr. Srinivas, sir. So thank you very much, sir, for the nice session. So I have a question, sir.
Yeah, please.
Yeah. Sir, actually, as per the industry, please tell us, means what are the, what are the skills that are required to enter in a industry for EV, in a EV industry, sir, specifically?
So as I mentioned in my presentation, for electrical engineer, I'm giving some examples. So as
Yeah, for
we
yes, sir.
yeah. For power electronics, as I mentioned in the architecture of the EV system, so where we require the power electronics knowledge, so where we need to develop from the different converter like AC to DC or DC to AC. So this converter, the basic knowledge of the converter we required, and what are the standards they are following. So if every country having a different standards, so to maintain their country pollutions, air emissions, so environmental. So according to that, they can go through some standards for the countries. And for the power supply, so like a chemical engineering people, so they have a different area where they can explore more related to the which kind of chemical batteries will be providing the more energies. And the charging systems, as I mentioned in the starting, so we required some renewable energy sources like wind, solar, non-renewable energy sources which can to charge it. So there also we can do it. This can be, so you can utilize from any kind of software like your Simscape, or you can use for the MATLAB. This basic skills is sufficient to entering into the any industry, I believe.
So coming to the softwares means if we see the confinement of the rural level, the softwares which are available means which type of what are the softwares that are very much required to get the skills, sir? Means MATLAB you told.
Yeah,
Apart from-
MATLAB, as I mentioned, so I think maybe for most of the people, I believe from academics, so very feasible and accessible software for you. It is like a MATLAB, so you can utilize MATLAB for to develop this kind of models. So your converter, inverters, or the renewable sources, anything you can do it. You can also do from the DSpace, Typhoon Hill. There we can develop some embedded systems kind of system. You can get some hands-on experience. So when you're developing some few prototypes.
Okay, sir. Okay, sir. Shoot, sir. Participants, please, the final call, please interact with our sir. If you have any questions, even you can post your questions in the chat box also. We will see. Yeah, we'll be sending you the feedback links, definitely. If you have any questions, please interact.
I think there is no question.
Oh,
It's
yes,
very
yeah,
clear
yeah,
for
yes,
them,
sir.
or there is nothing understanding them.
Yes, sir. Okay, sir. With your permission, we'll be closing the session, sir.
Okay. Thank you.
Thank you, Dr. Srinivas, sir, for this highly insightful and futuristic session. Your perspectives on the energy and EV ecosystems and BMS specifically have truly inspired all participants a lot. And with this, thank you very much for accepting our invitation and being a part of this Atal FDP, sir. Thank you very much.
Yeah. Thank you, Vishnu College, and all the participants for joining this session. We'll look into in the future some upcoming sessions also. Thank you all. Have a good day.
Sir, definitely. It's our pleasure, sir. Thank you, sir. Thank you. Click, sir. Okay. So, dear participants, with this, we'll be concluding our session 11 of our Atal FDP. Now we'll be moving on to session 12, which is on the MATLAB-based PMSM drives for specifically EV applications. So now we have a resource person in the meeting, and we request our resource person to please take over the session, sir.
Yeah, thank you, sir. So am I audible?
Thank you, sir. Yes, sir. You're audible, sir. Thank you, sir.
Yeah. I hope my screen is visible, sir.
Yes, sir. Visible, sir.
Yeah. 1 minute. I hope my screen is visible, sir.
Yes, sir. Yes, sir. It's visible, sir.
Yeah, all right. So
Please
yeah.
go ahead, sir. Again, welcome
Yeah.
again, sir. Please go ahead,
Yeah,
sir.
yeah, yeah. Thank you, thank you. Yeah.
Thanks.
So yeah, very good evening to everyone. And today in this session, we are going to see this PMSM drives, with the help of MATLAB. Like wanted you to see, like we have PMSM drive. Okay, this is our PMSM, and we want to control the PMSM for EV application. This is the control strategy based upon SVPWM and field oriented control. Okay, so we'll discuss this, how we can make a, how can you model this, and also we try to extract the renewable energy from like multiple sources, like main source is the battery, and we have a battery here to support the dynamic performance, to enhance the dynamic performance. Some companies, they are also working with the integration of supercapacitors. Okay, so try to integrate supercapacitors and it's in the main battery, and also some of the power we try to extract from the solar. Okay, so the complete system with these three sources, we are trying to run this PMSM drive for EV applications. We are going to discuss in this slide. First, try to understand more about the PMSM and its modeling. Once you understand it, then this side you will be very much clear. Okay, and then you already, like with the help of renewable energy sources, I think you have some sessions on renewable energy. So with the help of that, you can make a DC link, and that DC link we try to utilize to drive this PMSM. Okay, so we'll go step by step, and how can you control such a big system, like you have three sources, we need to coordinate them to make a stable DC bus, and then try to ran this PMSM motor as per our wish, like and also if time permit, we can also see various control strategies, like here we have PMSM, and also we have, sorry, for PMSM drive we have done with sliding mode control and synergetic control and and PA control, like that we are having. So we'll see step by step. Okay, so before going like before going further, like I like to discuss something on you should know the ratings of the PMSM which we are designing for the EVs. Okay, these four-wheelers. So you can see that the peak power ratings of motor, like you can see 165 kilowatt motor they are using in Tata and hybrid Camry and Prius. Like you can see that they are in the range of more than 50 kilowatt motors. Okay, so even up to 165. Even if you go for this Tesla, they are going up to 560 kilowatt power rating motor. They are using it. Like mostly, most of these four-wheelers, they are doing with the help of this PMSM. Okay, so we try to understand there is several advantages if you choose the PMSM, and once we have chosen with proper justification for this electric vehicle, then we will see that how we can control it. Okay, to control PMSM or any motor, we should have a strong background on the mathematical modeling of that particular motor. We'll see that. Once we understand that, then we can go for the development of closed loop control and then integrating with these sources in addition to the battery. Okay, so we'll see that. You can understand. You can also see that their speeds are in the range of like very high speed RPM, like 10,000 RPM, and the Newton meter you see that it is around 300. Okay, so okay, what I wanted to say is that for this kind of electrical vehicles, a four-wheeler, we need motors of a very high ratings. Okay, so first of all, since our topic is here, we are discussing more about these four-wheelers. Okay, so in these four-wheelers, you should understand the requirements of the power is very high, and also speeds and torques also very high. That is what we could have noticed from the existing motors what they are using in electric vehicles. Okay, so like there is, like, as you know, that there is a two type of magnets we can, like, one is the permanent magnet and second one the electrical magnet, right? So now we are talking on this permanent magnet based machine, right? That is, we are talking about a PMSM, right? So why we have to go for this? Okay, there is, like, typically permanent magnet machines, in that we are having PMDC and BLDC and PMSM. In those cases, we are using a permanent magnet. Okay. So why we have to go for the permanent magnet based technology? We have to first understand that. Okay. One thing is that uh, in case of a PMSM, okay, we are using directly a permanent magnets. Okay, since we are using a directly permanent magnets, we are not requiring any kind of a winding to build the flex. Flex is already inherently it is there, right? So because of that, there is no, like in case of synchronous machine, this is a PMS. In case of conventional synchronous machine, we are going to excite the winding, and then we are going to build the flex. But in case of PMSM, since we are using directly magnets, because of which we doesn't need any additional excitation to produce the flex. Okay, so that is the first point. Okay, and now electrical energy is absorbed by the field excitation system. Because of that, there is no losses. Okay, there is no any kind of excitation losses. Okay, so that is a advantage of this in case of PMS. Okay, and since in case of electromagnet based machines, what will happen is that when you are exciting it, it will take some time to build the flux. Okay. And then once you are having the flux on the rotor, also flux on the stator, the interaction between these two, then we will be having a the torque. Okay. So it will take some time. Okay. Once you are giving a voltage to the winding, and winding it will take some time to build the current, and then flag, means MMF, and then flags, all these things will take its own time. Okay, maybe in milliseconds or something like that, depending upon the winding parameters. Okay, so but what I wanted to say that it will take some time to build the flags, and there is an interaction between these two flags to produce the torque. Okay, but since already you have permanent magnet, so this time is not required. Okay, so since already flex is developed, by default flex is always there. Okay, so as soon as we are giving it is like that time is taken for this development of the flex on the rotor is now becoming 0. Okay, so means what I wanted to say that it is having a very good dynamic performance, means very fast. Okay, uh, dynamic performance is better than electromagnetic excitation. Okay, and also we doesn't need any. Okay, yeah. So dynamic performance is good. Since we doesn't need any kind of a binding, okay, the construction is very much simpler, okay, and maintenance is easy, and okay, so these are the advantages in case of permanent magnet based machines. Okay, because of all these advantages, we are trying to move towards the PMSM, and also because we doesn't have on the rotor, we doesn't need any kind of a winding. It doesn't require more space. Okay, so because of which it will become a compact. Okay, our machine becoming a compact. Okay, and torque by weight ratio, a power by weight ratio. Okay, means within the less space you are able to produce a good power compared to other competitive machines like synchronous, conventional synchronous machines and so on. Okay, so this is also high. Okay, that is another advantage. Okay. And also weight of the machine will be high because you are not using it on the rotor directly, you are keeping permanent magnets, and in case of electromagnet you need to keep a core on that, you need to keep some kind of a conductors. Okay, so that copper wires you need to wound like a winding, and also that is also increase the weight, but in this case weight is also less. That's why the torque by weight ratio is better. So by all these advantages we in case of a EV, we know that we want very compact solutions. Okay, the solution whatever we develop, especially for the EV, that should be compact and lightweight. These are first priorities. Okay, so that's why we are particularly most of the manufacturers. Okay, they are mostly they have adapted PMSM. Okay, and then induction machine or something like that. But most of the members they adapted the PMSM. That's why in this session we are discussing more about this PMSM and then how to make PMSM based drive for EV application. Okay, first it should be very much clear that why we are going for the PMSM in case of EV. Okay, so we have discussed all the advantages which are offered by this PMSM. Okay, and mostly these BLDC and PMSM, okay, based upon the flux distribution, there these two means like there is a difference in the construction because of the flux distribution is different, and if you see it in the MATLAB, the machine is same, but based upon the back EMF, we can see that if back EMF is trapezoidal, it will be configured like BLDC. If the back EMF is sinusoidal, the same motor will be configured like PMSM. Okay, that is the difference in the MATLAB. Okay. So, okay, these are the advantages I have discussed. Okay, anyway, I kept it here so you can see that. And also, we say that it is a sine. PMSM is also having another nickname called sine wave brushless DC motor. In can normal BLDC motor, the what kind of back EMF we will get? Trapezoidal. In this case, sine wave will get. So, sine wave BLDC machine also called the PMSM. Okay. So because of its compactness and less noise and tolerables are low in case of PMSM, so it is used in several applications, not only in EV like that. It is also used in several applications like industrial drives, farm plant, blowers, noise, in addition to the EV. But anyway, our topic is here. We need to understand for EV applications. Okay, so if you see the basic difference with the our construction wise, it is like stator. It is same like our synchronous motor. The main difference is the rotor. Okay, so construction wise. Okay, As I said that in case of a PMSM, we are going to get a back EMF. You can see that it is a sinusoidal. Okay, because your flux density is also sinusoidal. Okay, you see here in case of a BLDC, we will be having this kind of a trapezoidal back EMF. That is the difference in case of PMS and BLDC. That is what we have discussed in the even in the MATLAB. I will show you in the MATLAB. Okay, so we try to excite the windings when we are having a flat back end. Okay, in this region, you see that the current is, this is the current waveform. Okay, this is the back end waveform. Since the current is here, so we will be having a flux of flux density in this current during this period. Okay, so this is the main differences in terms of flux, current, and the back EMF in these two machines. Okay, so you can see here, like you're having sinusoidal back EMF, and here we are having trapezoidal back EMF. Okay, so since we're having a sinusoidal back EMF, we are also going for this vector control. Right, we are discussing here actually. We are going to discuss field-oriented control, and this machine is very good for precise motion control and high power applications. Okay, in case of typically two-wheelers, we are going to use these two-wheelers and three-wheelers. Where there is a low power requirement is there, we prefer BLDC, and here in this case, four-wheelers and above, we mostly prefer this PMS. Okay, so why we are going to see what is the difference in terms of their construction also, we'll see that. Okay, so and if you see the torque, if we compare in between these two in terms of a torque, we will see that. Okay, so we have, in this case, we have a very good torque production. Okay, so you see that. So we are having the sinusoidal back EMF, and if you're given, like if you're controlling the current and whichever that they are in something like that, then you're going to get in a phase so cos square omega t. I've taken a cos in terms of the cos. Okay, so EI is nothing but E cos omega t. II is I cos omega t. So if you multiply EI cos square omega t, you will get it. Like similarly in the B phase, EI cos square omega t minus 120, and this minus 240. Okay, if you sum total power, it is nothing but 3/2 EI. Okay, mathematically I kept it here. Okay, so cos square omega t is nothing but 1 plus cos 2 omega, cos 1 plus cos 2 omega t by 2. That the 2 I have sent it here. Okay, same thing here, 1 plus cos 2 omega t is 120. That 1 by 2, right? That 1 by 2 I taken again. So if you simplify it, cos 2 omega t plus 120 cos 2 omega t plus 240, these sum of these three will become 0. So we'll get 1 plus 1 plus 1, 3. 3e by 2. Okay, this is the torque, total torque. Okay, whereas in case of BLDC, you will get more torque actually compared to this. Why, we'll see that. But what is the problem here? Your distribution of the flux is very sinusoidal, and you will be able to get a constant torque. Because of that, the torque ripples will be low. Because of that, your noise is very low. The BLDC, you can notice that they are very less noise they will produce during the operation. Okay, but in case of a BLDC, you see that how we'll excite it. We have a back EMF. We have discussed that the back EMF nature is this trapezoidal, and we are exciting the windings. Okay, during the flat region of the back EMF. Okay, so when we do this, okay, if you multiply this, then this constant into constant, you will get a constant here. Even there is some back EMF, but because current is 0, you will get a 0. Okay, So like this, we will do it for other phases also. Okay, whenever there is a flat, we will be able to the current will be we will give the current during the flat back EMF period. We will exert that. Okay, so we are with the help of the Hall effect based upon the position. Okay, of your rotor, we will exert the corresponding phases. Okay, so. So your back EMF will be like this. So out of like 180 degrees, or out of 360, if you take it, 240 degrees means or out of 180, 120 degrees will be there is a power, and 60 degrees there is no, means zero. Okay. So like you see that the power nature is here, it is a discontinuous. Okay. The power nature is discontinuous, and if you total power, if you find it out here, EI, it is a constant, and here it is a EI, and here it is 0, 2 EI. Okay, at any time of 0 to 60 or 60 to 120 or 120 to 180 or any time, sum of all the phases will be 2 EIs. Okay, here it is 0, here EI, and it is 0, so total is 2 times EI. Here it is 0, EI is there here on B phase, and C phase EI, so 2, and all the time you are going to get 2. Okay. So that's why you are going to get more torque compared to your PMSM. Okay, compared to in PMSM, you are getting 1.5 times. Here you are going to get 2 times. Okay. So because of that, what happens is that although you are getting more power, means power density is more. Okay, so you can say that power density is more in case of a BLDC, but also the torque is also more. Because here in case of these VRs, you can see that both voltage and currents are sinusoidal, but here you can see that your currents are non-sinusoidal and vacuum. These waveforms having actually, if you see the application of Fourier series is that any periodic signal you can synthesize in terms of multiple order frequency components. Okay, so you can see that this waveform, either it is a the Cauchy square wave or trapezoidal wave. Apart from the fundamental sinusoidal component, it is also having some other harmonic components. Okay, that may create some kind of a noise. Okay, so that's why although it is a power density is good, but there is a problem with the little bit more noise compared to PMS. Okay, so that is the comparison also I kept it here. So these two machines, one is PMSM and second one is VLDC. Mostly they are same, PMSM and BLDC. Only the difference is that a little bit difference in the rotor construction, because of which you are going to have a flex distribution in the space is different. That is one. Because of that, your back EMF will be different. Only that is the difference. Okay. So we'll see that. Here, currents like are sinusoidal in case of PMSM, in case of VLDC, it is a quasi spherical. That is what we have noticed here. Okay, how we'll get sinusoidal or quasi spherical? We'll bit see in the coming slides. You will see that. Okay, so like RMS, if you see that it is like Im by √2. Okay, because you have a sinusoidal current. RMS, if you want to find it out for sine, it is a Im by √2. Okay, whereas in case of BLDC, it is like as I said that you are having a constant current. If you take it, if you wanted to find out the RMS value for this kind of a Cauchy square wave, okay, so where you are having 180 degrees. Out of 180 degrees, 120 degrees, we are having the current. Okay, the current magnitude, let me say I peak. Okay, so 120 into I peak into 0 times of 60 degrees by total time period. Okay, the whole if you like you would be knowing the shortcut, I just directly writing I peak times of the 120 degrees by 180. So it is nothing but √2 by 3 I peak. Okay, so your currents also. So like we have seen the torques, we have calculated power, we have calculated in case of the power in this BLDC it is more, it is like 2 times of EI, but here and here it is like 1.5 times of EI. Okay, so okay, so you can say that more power for the same space, same value, then we say that power density is more in case of BLDC. As I said that torque pulsations are less in case of PMSM and more in case of BMSM, okay, because of this back EMF nature and currents. That's what we have discussed. Okay, so back EMF is angle and okay. Windings like here, since we wanted to have a sensual back EMF, typically we will keep a distributed nature winding. At trapezoidal case, we will keep a concentrator. Okay. So this is the thing. Okay. So this is a major difference between PMSM and BLDC in terms of various parameters. Okay. So something here. So this is the power output by ratio. Then PM in case of a PM, BLDC it is having higher, like 1.15 times compared to the PM. Okay. So that's why like we can say that power density is more in case of a BLDC, but only the problem with the torque ripple. That's why you will need a smooth speed in case of a BLDC compared to a PMSM. Okay. So you see that like these machines, whether it is a PMSM or BLDC, needs a power electronic converters to exact them, okay, and to control their speed and torque. Okay, so we try to make them as a drive. Okay, so if you see that we have these are the various parts. Okay, this is our like. This is like rotor, stator, and their housing, and then we are having a power electronic, like controller. We say it is a power electronic converter. So to which we are going to excite the winding based upon the position. Okay, right. So that is essential. So okay. So now we'll see that, as I said, that the stator construction, whether it is this PMSM and a conventional synchronous motor, okay, the stator construction is very much same. Since you are already familiar with the synchronous machine, whatever stator is there, the same similar kind of construction there in the PMSM. Only the difference is with the motor, and when you compare with synchronous motor. Okay, and even in case of PMSM and BLDC, again there is a lot of construction only. There is a little bit difference. Okay, based upon that, the rotor. Actually, what we are doing in case of this PMSM or BLDC, on the rotor directly we are placing the magnets. Okay, based upon the arrangement, we have a 3 different types of rotors are there, called surface mounted, or surface outset, or surface inset, or interior. Okay, there is a 3 types of rotors are there in this permanent magnet based mount. Okay, called surface outset means on the surface you will keep your permanent magnets, or surface inset, like okay, surface outside or surface in on the surface inside you will place the you will place your permanent magnets. Okay, or else interior you will place somewhere. Okay, so there is a 3 ways. One is the surface outside and surface inside and interior, or buried type. We also say it is a buried type of PM machine. Okay, a buried type machine. Okay. Right. So based upon this, there is a based upon this construction difference in the rotor of these 3 arrangements, will have a different different things we will get it. So let me show you. These are we have discussed. Okay. Yeah. So here the construction of a PMSM starter is like is same as that of synchronous motor. That is what I told. And these you see that in case of we have different types of permanent magnets we are using where with high permeability. Right. So like these are the some type of materials. We say it is a rare earth materials. Because of the rare earth materials only the cost of these PMs are quite higher. No. So okay. So and based upon this rotor, only the rotor construction is different from different in case of some okay. So this is a permanent rotor type, permanent magnet machine rotor types are surface mounted or is also we say it is surface outside, surface inside, or interior or buried type. Okay. So if you see in more detail about the starter will be like this. Okay. This you would have seen that the same starter kind of a structure we are using in the manual or synchronous machine or PMS machine. Okay. So right, and the winding, the way you wind the synchronous machine, the similar way also we will wind place the winding in our PMS also, right? So so we are having the sinusoidal MMF we want, so we'll go for the distributed winding in case of a PMS. In case of BLDC, you can go with the concentrated winding. Okay, so that I'm not going to deep about the machine design. Some of my students also they have done the machine design in the ANSYS. Anyway, so our topic is here is talking about the PMS simulation drive. We'll go through some basics about motor since we should know that how they are different from the conventional motor. So that's why I'm trying to compare this motor with the conventional machine and then what are the difference and how we can model these machines like mathematical model because we wanted to make a drive because we say the drive means some power law converter will be there. To control the speed of your machine parameters, we need a deeper mathematical understanding about the machine. That's why just once you know the little bit basics about this machine background, then we'll go for the modeling. But modeling is very much important. Once you understand the modeling, then you can make a develop a closed loop, easily closed loop control of the this drive. Okay. So yeah, as I said that you can see that there is a the way we place the windings is that on the surface also directly there is a line. Okay. This is like inside. Okay. There is different pictures of the PMS and rotor. I kept it here for what we have discussed earlier. How the based upon the way you are accumulating your permanent magnets on the rotor, there is a okay. So
Please continue, sir.
thank you. Yeah. So all right. So it is like that. All right, so there is these three types. Now we'll compare them. I'm not going more in deep about these rotor constructions. We'll compare them, but we should understand which type of rotor construction we are taking in case of this PMSM. Okay, so we'll see here. We can see that this is the on the rotor surface we are placing the magnets. Okay, since we are placing the magnets on the rotor surface, what happens is that when machine is rotating there is a lot of mechanical stresses may be there on your magnets. Okay, because of that there is a possibility of because of the centrifugal process and all there is a possibility of these magnets may dislocate. Okay, that's why these machines we cannot go for the higher speeds. That's why it is used for only low speed application. This kind of a rotor construction. Okay, what is this surface outset? Okay, surface outside machines generally we are limited to the low speed. Typically, we use this kind of a thing in case of our BLDC. Okay, because this is very. But the advantage is that it is very easy to design the rotor. Simply, we are having this rotor on the rotor. We are placing our magnets. Very easy. right? So it is not much robust. Yeah, it is not robust because actually what happens when the rotor is rotating, what happens is that there is a centrifugal force acting on this magnet, then there is a possibility of dislocation. Because of that, the mechanical strength, the mechanical protection which are giving to this permanent magnets are less. Right, so that's why they are not that much robust. Okay, so and the air gap is uniform throughout the space compared to other. We'll see that. Okay, compared to other winding. And the next one is that surface inset. Okay, what we do, we have a this kind of a rotor, like, and then we will place, we'll cut it, and then we'll place the windings inside this. So we will remove this portion and we'll place the magnets like this. Okay, so just we'll place on the surface. Okay, so like this. Okay, just inside the surface. And another case is that what we will do, we'll place the magnet inside. Okay, inside. When you are placing inside, what happens is that, like you can see, that we have placed the magnet inside. When we place the windings inside, what advantage is getting that they are very much mechanically protected. Right, your magnets are like well protected by your rotor. Okay, so then what happens is that even you go for high speed applications, even there is a centrifugal forces out there that may not disturb your magnets. Okay, they are well protected, so you can go for high speeds. That's why this buried type or interior type machine can go for very high speeds. Typically, we use in case of PMC in this kind of thing. Okay, because we have seen that we need like 10,000 RPM, and one model they're using 6,000, and then like in top high speed one they're using 300 RPM and 10,000 plus, sorry, 300 Newton meter and 10,000 plus RPM. Okay, so you need very high speeds. Okay, so in this type of speed, generally we are going for this kind of a rotor construction. Okay. What is the problem is that the accommodating of this permanent magnets are a little bit difficult than these two. Okay, they're like surface inset is the moderate in between the surface outset and interior. Okay, it is having a mixed behavior, like some advantage from this and some advantage from inside is there in case of this surface inset. Okay, so surface outset, what is the advantage that you can easily design the rotor, because directly we are placing the magnets on the rotor surface itself. It is very easy, right, to place the permanent magnets. Surface interior means it is like interiorly you need to put a slot and then you need to place your permanent magnets. Okay, that is difficult than the first one, right? In this second one is like it is a medium. Okay, the difficulty level of accommodating your permanent magnets is medium in case of a surface inset. So this is the like major difference between these three type of rotors. Okay, so now I am comparing these. Okay, so these are all features I kept it in previous, but I already discussed. That's why I just put that in the past. Okay, so what we are doing is that we are comparing surface outset, means surface mounted. Okay, and then there is a buried type or interior type. Okay, the construction is very simple, as I said that. Okay, because on the rotor surface itself, we are placing your permanent magnets. Okay, and buried type is relatively complicated. We are comparing only these three, right? Among these three, this is relatively complicated. Okay. In case of in case of the surface mounted, the armature reaction flux is small, and whereas in case of buried type, it is high. Okay. Permanent magnet protection against the armature fields is less, and here it is more. Like because your rotor permanent magnets are inside, right? So eddy current losses in the permanent magnets will be there in case of surface mount, right? In buried type, they are well protected. Eddy current losses also the permanent magnets. So like because permanent magnets also having some kind of a conductivity, right? So right and dampers in case of surface mounted it is expensive, and in case of buried type it is less expensive. Okay, based on this we found this is actually typing mistake. Okay. Suitability of these rotor configuration, surface mounted mostly will prefer for the BLDC. Okay, and buried type will prefer for the PLDC. Okay, they are very much suitable for high speeds. They typically compared to BLDC, in case of PMS, we go for the high speeds. As I said earlier. Okay. So BLDC and this one is having mixed behavior. It can be suitable for both BLDC and rotor complexity is low because of the constructional advantages which we have seen it. So in this case, it is very high. Flux distribution is here, it is a square wave, here it is sine. Okay, the speeds we can go for very high speeds like 2 to 3 times of the rated speed. Here you cannot, if you are going more, then there is a possibility of dislocate the windings. Okay, these are the major difference between the constructional things. Okay, so typically in case of PMSM, either you will take this kind of rotor construction or this. Okay. So for what we have seen is that we have seen the rotor types in case of these permanent magnet machines, and we have seen previously some advantages of this PMS. Okay, so we have discussed all the things about positives, but what do you think that there's no negative side of this permanent magnet machines? Yes, there are some drawbacks because we are using a rare earth materials. Okay, rare earth materials. So these rare earth materials, they are expensive. Okay, that's why the permanent magnet cost is little bit higher. Okay, because actually what the China people have done is that Chinese, they have imported from various countries, like India, Brazil, and some South American countries. Okay, they have imported and they have a lot of resources for this permanent magnet future. Like if you are going for this PMSM or BLDC means what happening is that you're having some dependency on these Chinese people, right? So that's why some people they are working on some alternative machines. Okay, but since the PMSM is having a better performance, that's why people are working with the PMSM. But on other side, like some countries, they are trying to develop on without dependency on these rare earth materials. Okay, so like switch reluctance motor, synchronous reluctance motor, right? Like something like that they are trying. But anyway, at this moment, this PMSM machine has a very good performance compared to other. That's why we are most of the companies they are trying to do. That's why we are exploring this in this session. Okay, one is that the cost is very high, and magnetic corrosion, and there is a possibility of demagnetization. Okay, and aging effect is there in case of this permanent magnet machine. Okay, so yeah, so these are the things about basics of the. Now we'll go for the modeling. Okay, so in case of permanent magnet based machine, what we are trying to do is we are trying to model this machine on the DQ frame. Okay, we can model it on directly on ABC frame, means actual quantities, or you can convert them like with some kind of hypothesis model. We will try to develop. Actually, what we are trying to do, actually, IA, IB, IC, we have like what are parameters, maybe currents or voltage or currents, three-phase quantities. We are trying to convert into some two-phase quantities which are like 90 degrees apart. They are equivalent. Okay, you see whatever resultant you are getting with this ABC quantity, the same kind of results you should get with the liquid. Then we say that they are equivalent parameters of these ABC parameters. Okay, so there is some advantages with this two-phase model. Mainly, you would be knowing already. So the speed control is very good. Okay, in case of if we compare conventional machines like DC machines here. Induction machines and synchronous machine, the speed control is very good in case of a DC machine, right? So typically for the speed control application in conventional cases, we use either DC machine or induction machines, right? Because like in case of synchronous machine, what you need to do now, we have a parallel time. Now it is possible, like if you wanted to control the synchronous machine speed, that is nothing but MR is equal to NS is equal to 120 F P. So you need to we need to go for the frequencies and that pole. So pole changing is not good just while in the operation. So generally, if you wanted to vary the synchronous speed, what we need to do, you need to go for the frequency change. So that needs some kind of a power return. Because of advancement of power, now we are having a very good control to the synchronous machines also. Like even in earlier days also, like in induction machine, we can control the speed of induction machine easily. Why? We are having NS is equal to NR is equal to NS into 1 minus S, right? So this NS is equal to 120 P. We have different speed control like frequency control, pole changing. This S is depending upon if you see the torque equation, torque is equal to 190 by 190 by 2 pi ns into s square r upon r2 square plus x2 square, right? So because of that, you will be this torque is the slippage function of voltage, and we have seen that V and F speed will be affected. Then slip is affected means slip or speed is getting affected. So we can go for V by F, right? Voltage and frequency, and then we can go for rotor resistance, right? A rotor EMF injection, like that. There is a various methods are there, and also there is a this vector control techniques also there. Anyway, what I wanted to say is that in conventional way, conventional machine, the speed control is very good in case of a DC machines. Although we are having several techniques of induction machines are there, because actually the main reason is that your field and armature, they are decoupled in case of a DC machine. Whereas in induction machine, your rotor quantities and certain they are not decoupled. Okay, so if you are changing one, a second quantity will get affected. Means you will not be able to control the torque and speed in a decoupled way. Okay, in DC machines, it is very good. You are having a very good decoupled control, so you can easily control the torque or speed independently. Okay, so that's why these machines are very popular for the speed control machine. But nowadays, because of the advancements in power electronics, we are trying to mimic the speed control of induction machine very closer to the speed control of the DC machine by using some kind of a this what is this hypothesis model they have developed. Okay, with the help of that, you can control the speed, which is very much similar to the DC machine, by transforming your ABC quantities into the DQ frame. Like there is a concept of clock transformation and clock transformation, right? So there is a rotating frame and stationary, rotating from synchronous rotating. Like that, there is a different machine modeling techniques on the different rotating frame theories are there. If the rotating frame is rotating at rotor speed, then we say that it is rotor reference rotating frame. If the rotating frame is rotating at synchronous speed, with synchronously rotating reference frame, we say, right. And if a rotating frame is rotating at any arbitrary speed, we say that arbitrarily rotating reference frame. And if rotating frame is at rotating at zero speed, we say this is stationary, stationarily rotating reference frame. There is a four rotating reference frame theory concepts are there. Okay. So we'll realize what I wanted to say, that all these cases we wanted to have some kind of a rotating frame, right? So we are trying to convert these three-phase ABC quantities into some new frame that we say it is a DQ frame. We are trying to model these quantities in the DQ frame. Okay, so for this, what we are doing is that we know that the voltage equation, right? This is like on the ABC frame, I am writing that the voltage is nothing but V is equal to IR plus the rate of change of the flux linkages. Okay, this is the basic equation of the voltage. V is equal to IR plus dψ by dt. Okay, so the rate of change means backline. V is equal to E plus IR, right? So E is nothing but rate of change of the flux linkages. So V is equal to IR plus dψ by dt. Okay, so this is like basic equation of the voltage. stator voltage equation. Okay. What we are trying to do now, we are, if you wanted to write it for representing all the three phases. So this is like A phase is like here E is nothing but e power j 2 pi by 3. Okay. Is a is an operator to represent this 120 degrees phase shift. Okay, between the A phase, B phase, and C phase, right? So if you see, this is that combined voltage, right? And this is the current, and this is the flux linkage, right? This is the 2 by 3 VSA of T plus A is of T equals J 2 by 3 of VSB, because we are having only degrees phase between A phase and B phase and C phase. It is C phase, it is A square to 40, right? So VSA, VSB, VSC is nothing but they are the instantaneous voltages. Similarly, phase voltages, ISA, ISB, IC is the phase current. These lambda SA, lambda SB, lambda SC is nothing but your flux linkage on the stator. Okay. On the stator, we are having a physical windings are there. On the rotor, we have a permanent magnet. Okay. That is what we are having in case of this PMSM. Okay. So what is nothing? How will you get this on the stat? Like we are having, let us take this is the A phase. Okay. And we have a B phase. Wait a minute. So here we have A phase, and here, what is that? We have a B phase, here A phase, and here a C phase. And we have, let us take permanent magnet. Okay. So we have a permanent magnet. So in the A phase, if you wanted to write a flux linkages called lambda SA, okay. The A phase, what are the flux linkages are there? If you see, let me take another color. Okay. So what happens is that you are exciting this, let me go back. Okay, so what you do, you are exciting your A phase and B phase and C phase. Okay, so this is our three phase supply we are giving. So when you are giving this A phase, then what will happen? There is a currents will be developed, right? So current will be there on the A phase. Similarly, current will be there because of the B phase excitation. Similarly, C phase, there is a C phase current. So what happens when there is a current is there, and then there will be development of the flux. That flux is passing, and they will cut with the other phases also. Okay. So similarly, your main field flux is that is also cutting here. Okay. So you see that at A phase, on the A phase, let me take. Okay, this A phase, because of it, there will be a flux on the A phase because of its own phase current, and because of the current here, there will be a flux. That also flux is also linking here, and the C phase also flux is also linking here, and permanent magnet flux is also linking here. Okay, so if you want to represent lambda SA, you need to represent because of the flux linkages on the A phase because of its own phase current and B phase current component and C phase current and then main field flux. Okay, so that's why we have represented like this. Okay, so lambda SA is nothing but LIA time psi is equal to Li, right? Flux linkage is equal to inductance times of the current because of its own phase current and B phase current. We say that inductance is LAB and A to C, the inductance LAC, and then C phase current. And this is the direct permanent flux we are having. Right? That is on the rotor, we are having a permanent magnet. That the permanent magnet flux is linking with your A phase, that is represented with lambda RA. Okay. Similarly, you can draw it for lambda SB and lambda SC. Okay, when you write it on SB and C B phase also because of this own phase current, there is a flux development. That flux links with the B phase winding, and because of the A phase, there is a flux is developed. That flux is also linked with the B phase, and C phase there is a current that because of that current there is a flux is developed. That flux is also linked with your C phase, and similarly, your main field flux, main field means you have a permanent magnet that is also linking. That's why you are having these four components will be there on E phase. Okay, so like this we will write the lambda SA, lambda SB, and lambda SC. That should be clear. Okay, so here we say that this LA, let me take it. So here we say that this lambda AA, because of its own phase current, the flux linkage are in the one phase, we say that it is self-inductance. Because in A phase, the flux linkage in A phase because of the other phase, we say that it is mutual flux. LAB, LC, LCAC, LCA are mutual flux linkage, mutual inductances, and LAA, LBB, LC, say that it is self. All right, so this is how we will write the flux linkages. Okay, so similarly, what we do, we are having a permanent magnet and we have a field. So what is a lambda? This is the flux link and that is linking here. So what we need to write lambda r times of cos theta. And lambda RB means cos theta minus 120 and lambda RC is nothing but 1 minus 240. That it compared to A phase, B phase is like 120 degrees apart and that's why it is not like lambda r cos theta. It is like lambda r cos theta minus 1. Okay, this is how we will write lambda R, lambda RB, lambda RC. Okay, so now to model this, we need to know what is LAA, LAB, LAC. Okay, because we know that permanent magnet, because of the permanent magnet, the lambda R is known. Okay, when you bought the permanent magnet, so we'll be knowing what is the flux density, all these things, right? So because of the position, we will be able to call lambda R, lambda RB, lambda RC. But if we know this is not sufficient to find out the flux linkage on the A phase or B phase or C phase. Okay, if we wanted to find out the current, okay, we will give the excitation voltage. Okay, so to finding out the current, if you know the resistance and if you know this, then you will be able to find out the currents. If you know the current and voltage, you will be able to find out the power, torque, and all other parameters. Our main challenge is to find out the currents. Okay, how will you find it out? We are seeing it. Okay, so to find from this equation, these things are known. Okay, so we still need to find out lambda, LAA, LAB, LAC, all these things. Okay, so now how will you do it is that what is LAA? Okay, what is LAA, LBB? If you remember, maybe you would have modeled a synchronous machine. The similar way we need to model here. Okay, so we see that here. Let me see here. What we are having is that we are having a permanent magnet here. Okay. And we have a phase winding and B phase winding and C phase winding. That is what I have represented. Each phase, like all the phases, we will give excitation supply. When we are giving VAS, there is a IAS will be there because the winding is having some impedance, voltage is there, and the impedance is there, then current will be there. Right. So this EM cycle negative are given, then we are going to get right some current here. Similarly, B phase, C phase, right? These are we have discussed. So what happens is that what is our ultimate challenge here is that we wanted to find out LAA, LBB, LCC. Okay. Similarly, LAB, LBA, LBA both are same because it is a symmetrical machine. That's why LBA is same. And we need to find out LBC, that is nothing but LCB. Okay, LCA or LAC. Okay, so how will you find it out is that first of all, we need to find out the A phase, A axis on the A axis. What is the MMF? Okay. When we are giving excitation, then there is a development of the flux, and that flux will be there, and because of the flux, there is a MMF. MMF is equal to N into I. Okay, so there is a number of turns. We say that let us take the starter. NS is the number of turns on the each phase, and all the phase it is NS. Okay, so what we are having is that. The flux link that MMF is on the A phase is nothing but IAS times of NS. Okay. So what I wanted to find out, the flux linkage is on the D axis. Let me say my rotor is on the D axis and direct axis. We say that. Okay. I wanted to find the MMF on the this d-axis. Okay, that means that you need to project this MMF onto the d-axis. To project that, we wanted to use IAS NS into cos theta r. Okay, so now you know MMF is here. Okay, so MMF is equal to N into I, right? So once we know the MMF here, if we know the MMF is equal to, we know that S into phi. Okay, so we wanted to know the phi flex because of this MMF. MMF by reluctance. MMF by reluctance, or 1 by reluctance, we say permeance. Permeance times of MMF is equal to my flex. Okay, so what we are trying to do is that we are projected here because actually typically the machine manifest, they will give you the reluctance or permeance on the d axis and q axis. Okay, if you know the permeance or reluctance on the a axis, b axis and c axis, then you no need to do all these transformations which I am talking. Okay, but typically we will be knowing on the dx and qx. That's why what we try to do, we are projecting the MMF here, and we know the reluctance or permeance here. So MMF and permeance, from this we can calculate the flex. Once you calculate the flex, then we are projecting back to A phase. Okay, so this A phase flex is nothing but this one times of permeance. Okay, PZD. So we know that A axis flex is on the D axis. Now we are projecting back to the A axis. A axis flex on A axis itself. We are finding it. That is a pi air gap. Okay. So that is nothing but what we need to do. You need to project again, means we need to multiply with cos theta r. Okay. So what we are finally we have achieved. A phase flex means that is nothing but your area flex is nothing but ns. Because of this is because of only d-axis quantity. Okay, similarly we need to find out q-axis quantity also. Okay, so that is nothing but ns into ias into pzd into cos square theta r. Okay, similarly we need to find it out because of the q-axis. Okay, q-axis back to on the a phase effect. Okay, so if we do it similarly, then what we are going, this is we have calculated. Okay, and then this is because of the q-axis, it cos 90 plus theta, right? Because actually when you are projecting here to here, it is a theta, and here it is like 90 degrees is there. So when you are projecting this quantity here, cos 90 plus theta, theta plus 90, cos theta plus 90 is nothing but minus theta, right? That's why we here wherever you got cos theta r, here you are getting minus sin theta r. That is the difference because of the q axis quantity. This is the axis. So now what we are having, right? So so this is what we are having, a phase flex, right? So all right. So because of the dx and qx, by current, by dividing with the current, we will get the LL, right? Okay, so what we are having is that so far we are finding out a phase flex. Okay, so this is the flex quantity. That's why what we are trying to do, the entire thing, n into phi, this is your flex because of dx and q axis. That should be multiplied with n. N into phi is MMF. MMF is equal L into I. That's why NS into flex by current is nothing but your inductance. That's what we got it, right? So what we are trying to do, we are simplifying. NS is here, NS is here. So this NS I am taking common because NS is here also there and here also there. So I am taking common. NS into NS, NS square. In both the cases, we are having IS. That's why I am taking IS common. So what we are left here, PZD into cos square theta. And here we are having PGQ sin square theta, minus sin theta, minus sin square theta, right? So this is what we are having. So simplifying it, so that's why I use the color coding to easily identify what are changes, right? So what we are having, cos square theta is nothing but 1 plus cos 2 theta by 2. Sin square theta is nothing but 1 minus cos 2 theta by 2. Okay, this is PGD, this is PGQ. PGD times 1 plus cos 2 theta by 2, and plus PGQ times 1 minus cos 2 theta by 2. Okay, simplifying, like I am taking, this is the cost components and this is the stationary component, like DC quantity. So what I did, I'm separating cost components and stationary, right? So this is PGD here into 1 by 2 and PGQ into 1 by 2. That I have taken 1 by 2 common, PGD plus PGQ by 2, and cos 2 theta I have taken common. Then we are having PGD by 2 minus PGQ by 2. Okay. Yes. So this is what PGD, PGQ permeances, right? So this is the DC quantities PGD and PGQ. So I have PGD plus PGQ by 2. I am representing like a PG naught. Okay, and this PGD and PGD minus PGQ by 2. This is a cos 2 theta coefficient. That's why I represented like 2 theta coefficient. That's why we say that double line frequency. That is a PZ. Okay, I represent PZ. Okay, so what we are having, this is a PG naught, this is a PZ2. So your inductance profile is like this: LG naught plus LG2 cos 2 theta r. Okay, because what we have done, this is a P, this we have done a PG naught, right? So this is a PG2. N square, L is equal to what? N square by S, or else N square by P. N square by N square into P, we say that it is a inductance, right? So N square, that I represent like LG naught. Okay, LG2, LG naught plus LG2 cos 2. So the inductance profile will be like this. Okay, if you plot this, you will be able to get this reluctance profile, air gap, and it will be like this. Okay, it is like cos 2 omega t component. It is having average component as well as cos 2 omega t. Okay, right. So this. Now this what we are having is that air gap inductance. Right? This is. Okay. Similarly, we need to find it out mutual inductance components. Right? So what we are having this, because of this air gap as well as the leakage, we will get the total inductance. This we have found out this, and there's a leakage quantity, right? That will give you the total self inductance. Okay. So this is nothing but this LAL plus LG0 plus LG2. Like that, we are having other LBB, LCC. Okay. So they are having like 120 degrees apart. That's all. This is how we will be able to find out the self inductances of each phase. Okay. Now we are able to find it out. What we are trying to do is we are able to find out. So far, LAA, LBB, LCC, we have already done with it. So we need to do mutual inductance. Once you are having mutual inductances, right? Self inductance we have, the flex linkage we are having. So we will be able to find this flex linkage in terms of currents. So okay. So once we are having flux linkages in the currents and this current and the voltage we know, the parameters we know R and L. So we will be knowing all the things. This is the first order differential equation. By solving this, only one unknown current. Currents can be calculated. That is our aim. We wanted to find out the currents. Okay. Once we know the voltage and currents, we will be knowing the power. Okay. Once we know the power, then we will be able to know at a particular load torque, we will be able to find out the speed of your machine or drive. Okay, so that is our objective. Okay, so now I'm trying to find it out the mutual inductances. Okay, so mutual inductances. Now what you need to do is that first we need to, because of this currents in this space, we need to find out MMF, that you need to project it on D-axis, and then earlier we wanted to find it as self. That's why we are bringing back. Once you have done here MMF, and then once you find out the flex, now we need to project it to the B phase, not A phase, because we wanted to have LAB, right? So that's why this we are trying to do like this. Okay, so what we have done first, because of this current in this NS number of turns, we will get a MMF, right? N into I. Once we are having that, what we are trying to do, we are projecting on the D-axis. Right. So for that we need to multiply with cos theta r, NS IAS cos theta r. Once we are having here MMF, then we will be able to find out the flux because we know PGD and PGQ, they are known quantities typically. Okay, not PGA, PGP, PGC as I mentioned earlier. Okay, so like this, we are doing the flux by multiplying this quantity with PGD. And then what you need to do, we need to project it on here. That is what we have done. To here, it is cos theta minus 120 because here total is 120. Now we need to project from here to here. So it is nothing but 120 minus theta, right? So 120 minus theta. So that's why we need to write cos theta or minus 120 or 120 minus theta, both are same cos, right? Cos theta or cos minus theta, both are same. That's why I written cos theta minus theta. Okay. So it is like that. So this is because of the d-axis quantity. Okay. So similarly, now what we need to do, we need to find out because of the q-axis, right? So for the q-axis, what we need to do, cos 90 plus wherever it is there, we need to write cos 90 plus theta. Similarly, we have done this. Then total air gap flux, the similar way which we have done earlier, and just the calculations, everything we have simplified, and then we have done. We will be able to find out LAB. Right, so I'm because we are only left with 5 more minutes, so just I'm doing fast. So we are having LAB will be like this, simplified by simplifying it. Okay, so means your mutual inductance will be like this: Lg naught times of cos 2 pi by 3 plus Lg2 cos 2 theta minus 2 pi by 3. Okay. So once we are LAB, LBA both are same as I said that because we are having symmetrical nature. What we have calculated here, cos 2 pi by 3 is nothing but minus of, that's what we have to do, LG naught plus LG naught plus cos 2 pi. So similarly, we can find LBC is nothing but LCB, so that you will get like this and LCA like this. Okay, similar pattern we follow. Okay, so once we have done this, so you will be able to, like, so far we have able to find it out LAA, LBB, LCC in the first step, and in second case we have find out LAB, AC, right, LBA, LBC, and LCA, LCA, something like that, right? Okay. So like this we have done. Now finally, if you are putting all these things, we are going to get, this is your inductance. This is LAA, this is your LBB, this is your LCC. Okay, this is your LAB, this is your. Just I am changing my notations here just for to make it more easy. That's why I changed the notation. That's all. Nothing else I have done here. Whatever we calculated earlier, the same things only. Just I changed the notation. Okay. So we got all the components for your inductance. Once you know your lambda is nothing but what lambda is L into I plus your rotor components, right? So we are able to find all the inductance matrix and IIBIC and lambda RA, lambda RB, lambda RC. That will give you the lambda SA, SB, SC. Okay, so that is what we are doing. Okay, so this is our LSS, whatever we got in previous, I kept it. Okay, so now this is our basic fundamental equation. From what is our ultimate aim is that we need to find out this IS. Okay, so this is what we have. This thing. So like this, this is actually we did it everything on the ABC frame. Okay, this entire thing what we have discussed so far, that is on the ABC frame. We are not using any transformation, right? So see, when you see it on ABC frame, your inductances are very much complicated there in terms of cosine theta when theta is changing. Then your inductances are keep on all the values of inductance with rather space they are getting changed. That is a big problem. That's why ABC modeling is not so. Okay. We now to find out the currents, what you need to do, we have this equation, right? Vs is equal to Rs into Is plus d. Now we know this lambda S is nothing but L times of L is now we came to know we found this L, right, matrix, and I. So it is nothing but V is equal to I. There is I matrix. V matrix is equal to I matrix into R plus we have what L dA by dt, right? Something like that, right? So this is the matrix. And then what we are trying to do is that now we have a first order differential equation. By solving this, we will be able to find out the current, right? By solving this, by putting all the values, what we have calculated so far, only unknowns are the current I, IB, IC, except that we will be knowing all other things. So you will be able to solve the first order differential equation and you will be able to find out the instantaneous currents on ABC phases, right? So we know our excitation, so we know these means we will be knowing the power. So at a particular load, you will be able to find out the speed. Like that is the ABC modeling. Okay. So similarly, now what I'm trying to do, I'm doing it on the DQ modeling. I'm not going in much deep because now we have very much time left. So if I do the similar process, now I wanted to show you that here. Finally, your DQ modeling, your voltage equations are like that. Earlier it is VA, VB is equal to something like RI. And you see that here it is the equivalent of your here it became a stationary one. Like it is like earlier it is like something in the cos of theta, something like that. All, but here you see the beauty is that here when you do it modeling in the DQ frame, things are becoming very, very, very simple. And you see that. That is the beauty of your DQ modeling. That's why we try to model the machine in the DQ. Right, VDV equation, VQ equations are very much simple. Now you will be able to easily find out IDIQ. Once you find IDIQ from by solving this first order differential equation, which doesn't contain any theta or something like that. Earlier in ABC, when you model ABC, it is these inductance matrices and all these things are functional of theta, and solving them is very tedious process. But here we are not consisting any these equations are not contains any theta, right? You see that here. Right. The things become so easy here, so that's why this modeling is very good. So we try to model it in the DQ, right? By solving these two equations, you will be able to find out IDIQ. Once you know IDIQ, VDVQ, you know, right? So what we will do, we'll find out the powers and the speed. Okay, that is how we solve the machine parameters, like different machine parameters. Once you're having IDIQ, if you want to find out the actual currents, we can use the inverse transformation, so we'll be able to find out IA, IB, IC of your machine. It is very easy if you model it in the DQ. That's why now by using this concept, what we try to do, okay, let me take one slide here. And put a slide here. Take it. So now once you're having a good understanding about the parameters of the machine, all the modeling, then what we try to do, we try to control the speed of this machine. Okay. So so what we need to have this, we need to control the speed of this machine. We need to have DC. The DC should be converted into so we are using some kind of power converter. So what we do, we sense this speed, okay, and we put the actual reference speed of our, maybe if you wanted to sense it in the RPM or radians per second, it is up to you. You can sense it and you can set your reference, okay. And then we need to have a PA controller. Okay, this PA control will set your IQ star. Okay, so we are having this IA, IB, IC quantities. We are sensing using this ABC phase quantities, and then we can convert IA, IB, IC into ID, IQ, right? So ID, IQ. Using this ABC to DQ transformation, we can do ID and IQ. That IQ you can give here, and since you are using a permanent magnet based machine, so your ID reference will be 0. So actual ID will be so you are using a PA controller here. Here using a PA. This is like another current control. This is outer speed control. This will give you the VD VQ. Once you're having VD VQ, you can convert into VA VB VC. From this VA VB VC star, we will be able to produce a modulation indexes. That from modulation index will give you to the PWM modulator. That will give my gate signals. That gate signals I will use it here to control the speed. Whatever I will set here at any desired torque, I will be able to get my desired speeds. So like this, we'll make a drive. Okay, and okay, and okay. So and then what I'm trying to do is that I am keeping a battery. This right. this battery voltage is low, that's why I'm using some kind of a DC converter. And this what we have discussed about the drive so far. So this I have discussed the control strategy for the drive. Right. So what I'm trying to do, this DC, what we have discussed earlier, that DC we are building, DC link we are building with the help of the battery. Okay. Typically batteries having a problem is that they are having very good energy density. Okay. Energy density is high, but their power density is low. Okay. So they will not be able to handle the high frequency current. When there is sudden good acceleration is there, when there is sudden change in the load or something like that, they will take own time to reach that value. So, but that's why we will not be able to get a very good dynamic performance. To do that, what we are trying to do, I am placing some kind of a super capacitor. Okay. So the super capacitor, DC to DC converter, and this I'm integrating with my DC link. Okay. And also what I'm trying to do, I wanted to use EV. On the EV, we have a chassis. On the chassis, I'm placing the PV modules. You can extract some of the power because this FDP is also related to renewable energy sessions are there. So that's why I try to integrate. Okay. This drive pod I have discussed. Now this entire system I am showing. Okay, in this simulation. Okay, so this is the complete system. Say that okay, you can see that whatever speed I have set here, based upon you see that I am able to meet all the powers. See, you see that what I do is that when this first one is the PV power, second one is the load power, and third one is the battery as well as the super capacitor. Super capacitor will be there. This purple color that will be there only when there is some kind of a disturbance is there. Okay, at point 3 I reduced my radiation. Then suddenly that high frequency component power is taken care by the super capacitor, and normal condition battery is taken care. So that the stresses will be reduced. So that you will be able to meet your desired torques and desired speeds. Okay, so whatever I set my speed, I am able to achieve. Even my irradiation is changed. Irradiation I changed. You see that at point 3 I reduced my irradiation. That's why my power PV power got reduced. At point 3 you can see that my PV power got reduced. And at point 2 I changed the load. Actually, I'm putting some loads, some load here. You see. At point 2, I have added some load. Apart from the motor and some load, I kept it on the DC link. But still, I am able to get whatever my input is reduced or my load, I put a more load. Still, I am able to reach my whatever speed I am intended. Okay, like this, you can control the speed of your PMSM EV drive. Okay, so as we are already out of the time, so I wanted to close my discussion here. If you have any queries, feel free to discuss. Hello.
Yes, sir. Sir.
Yes, sir. Yes.
So thank you, sir. Thank you very much. Thank you very much for this deeply technical and well explained session. Your expertise has provided a clear understanding of the controls and also the inverter fed PMSM drives with respect to the MATLAB simulings. So thank you very much, sir, for joining us and being a part of this FDP.
Yeah, thank you, sir. Thank you very much. Yes, sir.
So, dear participants, now we conclude the session 12 of our FDP. Now, we now move on to the final session of the FDP, that is session 13, which is by Dr. B.L. Narasimharaju, sir, Professor, HOD of EEE, NIT Warangal. So, the session is on grid-fed AC to DC converters for EV charging and LED lighting applications. So, Dr. Narasimharaju, sir, Hriday, sir, do we audible, sir?
Yeah, you are audible. Yeah.
Thank you, sir. Thank you, sir.
Yeah.
So with this regard, we on behalf of National Institute of Technology, Bhimavaram, and the part of AACT Academy, New Delhi. So we welcome you, sir. It's a grand welcome for being a part of this Atal FDP. Now, I request Professor Naveen to please introduce our expert. Over to you, Naveen, sir.
Thank you, Kasim sir. It's an honor to introduce the speaker of this session and an eminent personality, Professor B.L. Narasimharaju sir. Professor B.L. Narasimharaju is a distinguished professor in the Department of Electrical Engineering at the National Institute of Technology, Warangal, Telangana. He earned his BE in Electrical and Electronics Engineering in the year 1999 and ME in Power Electronics in 2002 from University Vishweshwarya College of Engineering, Bangalore University, and completed his PhD at the Indian Institute of Technology, Roorkee in 2012, specializing in bidirectional converter topologies. With over 2 decades of dedicated experience spanning teaching, research, and consultancy, Professor Narasimharaju has significantly contributed to advancing power electronics, renewable energy systems, electric vehicle drives, and energy conversion technologies. His research interests include high-frequency magnetic component design, modeling and control of power converters, grid-connected renewable energy systems, high-gain DC-DC converters, transformerless inverters, induction heating, and battery charging circuits for e-mobility applications. He has guided numerous MTech and PhD scholars and published extensively in reputed international journals and conferences. He has successfully led several research and consultancy projects sponsored by national funding agencies such as the Ministry of Education, DST, SERB, Imprint, Spark, and CPRI, with a cumulative grant value exceeding 4 crores. Noteworthy among these are projects on high-gain transformerless inverters for PV grid tie systems, SRM-based solar PV water pumping, high power factor induction cookers with direct AC to AC conversion, and low-cost watershed monitoring systems under Spark. In addition, Professor Narasimharaju has been instrumental in organizing GIN courses funded by the Ministry of Education on cutting-edge topics like multi-level inverters for industrial drives and non-invasive fault diagnosis of EV propulsion motors. His vast expertise, innovative outlook, and leadership in advancing modern power conversion technologies make him an inspiring and highly valued resource person for this Atal Faculty Development Program. Thank you, sir.
So thank you, Professor Naveen, for the wonderful introduction. Now, we request the participants to please join me in welcoming Dr. Narasimharaju sir for his concluding technical session. So thank you very much, sir. Over to you, sir.
Yeah. Am I audible?
Yes, sir.
Yes,
Sir, audible, sir.
Okay. I believe my screen is visible to you all now.
Yes, sir. Yes, sir.
Okay, fine. Thank you.
Sir,
Okay,
can we check the change? Can you
Sorry?
move the slide, sir, so that is it working or not? We'll just check it out, sir.
Is it now movable?
Yeah, yes, sir. Yes, sir. It's working, sir.
Okay. Thank you.
Okay. Thank you, sir.
Yeah, so very good evening to all. Okay, so
Good evening, sir.
let me share my inputs on this grid-fed AC-DC converters for LED lighting applications. Sure. Basically, see, the topic is like with respect to the lighting systems. Now, what we are talking about, the most prominent energy efficient lighting system, which is like LED lights, lighting systems. So with this regard, see what is the developments and what are the roadmap, what is the research path, what are the research motivations in this direction. So probably I'll give some light on these aspects. Yeah, so when I say this, why this is so important topic, why I'm considered this is like basically as we all, of course, we know this lighting system is also one of the major energy demanding element. So therefore, see, and otherwise, of course, in this lighting sector also, right from the inception, so there is a lot of changes have been happened right from its traditional way of lighting systems there on to present day. Sorry, just pardon me. In fact, of course, I am little down with my health, so therefore, even previous session I could not engage. Uh, Otherwise, I should have been engaged in the previous also. So kindly bear with for my inconvenience in that. Yeah. So well, this lighting. Aspect. If you just look at this is of course a little
What was the
old.
action when you look at Liam Livingston? Was he not providing the value that they needed, given that they have
There
Tim
is
David and
there is some background noise. Hello. Yeah. So I request the audience to mute their microphone.
Sir, it was a disturbance, sir. Please, we have muted all, sir. Please go ahead, sir.
Okay. Thank you. Yeah.
Okay, sir.
Yeah. Well.
Thank you.
So this, if you look at this this chart, pie chart, in which say clearly indicates the the energy consumption towards this lighting system also. Typically, of course, even it is much higher than this what is indicated here, because this statistics is maybe like a bit old, down to 10 years back, which I collected. Otherwise, a late, okay, even in at present, even this part could be even much higher side on this energy consumption towards this lighting system. So therefore, now this lighting application is not just only confined to the either the domestic or industry, this thing. Otherwise, even in the industry part, even in the outdoor, in the electric vehicles, automobile systems, in most of the whatnot, even in the entertainment, so decoration. So because of the uh, a very good advantages benefits of this LED device. So these lighting systems are taken a very popular place in almost all areas of applications, by not just confining to this the domestic lighting system. So that's the point. And if you look at this year, so this is based on up to the 2022 statistics as one of the researcher. So he presented this statistical data, the total installed capacity. It is like in the mega units, like installed capacity, almost see. That means the replacement of LED with the almost all other traditional lights. Traditional lights, so other lighting resources like the traditional incandescent, halogen, fluorescent, CFL, all such those are the the traditional one which we they have grown in their phase, and presently we are here in this the latest one, the the developed technology. This with respect to, if you look at these statistics, so progressively there is a huge growth, and even the growing developments in even further with respect to the replacement of this highly influenced or prominent LED lighting systems. That's the thing one can understand. So that is sorry. So then if you just if I look at the what are these different lighting resources which we have seen so far, and henceforth now what we are going to see as it is started from the inception, from the good olden days. These incandescent lamps were the first source of light what we have seen, and which is being used since long years. But however, see, if you just look at their the consumption of this electrical energy, and how much that electrical energy that is converting into the light, and the other remaining energy which is being wasted as a heat, and that is almost, if you look at this approximately a 10% of electrical energy is only converting into the light output of the lamp, but the remaining is wasted as a heat. Okay. Also, its lifespan is roughly 750 to 2000 hours. Otherwise, if you convert that into like months, like, okay, 4 to 6 months, or little higher side of that, okay, if at all. And the light outcome in terms of the efficacy, the lumens produced per watt, which is typically a 14 to 18 lumens per watt for this from this incandescent lamp. Okay. So if you look at these figures, it is like, of course, the present day, the efficient light systems, if you compare, this is like a significantly a poor performing device now, which becomes almost obsolete now in most of, unless until there is a specific reason which we can use for this incandescent bulb. Otherwise, it's almost like obsolete. So we replaced almost all by these energy efficient LED lighting systems. Also, as a progressively, the second generation of the lamp, which is called the fluorescent lamp, which is I can say this is the improved version of the first traditional incandescent lamp that provides the improved efficacy, say 50-80 lumens per watt, and as the lifespan also, it is better than much better than this traditional first incandescent lamp. So that is how we can understand from this. And however, in addition to that, this fluorescent lamp generally, so it comes with that the inside that tube, so that phosphor material which is been coated, okay, the toxic gas. But otherwise that is not an that kind of issue is not in case of this incandescent lamp. But however, in the fluorescent lamp, so the toxic material in that fluorescent lamp, which is not that safe to the environment and the human health as concerned as a part of its disposal. So that is one negative part of this fluorescent. Otherwise, as per its lifespan and this luminous efficacy, it is better than the traditional one. So that is one thing. And another the lighting resource, that means the other types of the lamp it was high intensity discharge lamp. This lamp mostly, which we have seen in this outdoor and the stadium lights, floodlights, all such, okay, in such applications, but not in the domestic front or the, okay. So, but otherwise, this type of light is also it is comparable to this fluorescent lamp. Otherwise, even it is a little better than the fluorescent lamp in terms of its lifespan as well as its the light output. That means the lumen output per watt. Also, this lamp is also, it's like not environmental friendly, and as per the okay, human health is concerned in terms of its disposal. That is the point. So also I wanted to mention here another thing. Another one is like fluorescent lamp. Conventionally, it has come with that conventional choke of like that a choke coil. What normally we are familiar with, and also a starter we used to familiar with, but otherwise it's a capacitor. So these two in the conventional fluorescent lamp, so the choke and this capacitor, and also it's okay, it's constructional. Okay, it takes larger side. It means that the size of that fluorescent lamp, even for that 60 watt bulb, okay, 60 watt fluorescent lamp. If you just compare that with respect to that some compact fluorescent lamp which we have seen, okay, that even, okay, which is much better. That means the compact fluorescent lamp in the sense where those conventional choke coil and these capacitors have been replaced with the uh, this electronic ballast. Electronic choke, which is so called. Sorry. So therefore, that CFL lamp, which is so called like a compact fluorescent lamp, and that's the improved version of the traditional fluorescent lamp. Okay. Of course, anyway, that which I have not just pointed out, mentioned here, but otherwise, there was one that was another improved version of the fluorescent lamp also. That is more compatible and also even much better efficiency in terms of the luminous efficacy as well as in that point. Okay. But however, all these traditional light sources now is override by the latest one that improved energy efficient LED lighting systems. So that is the one. See, what is our topic of now concern? All those traditional lamps are now replaced by with this advanced LED lighting system because of its various advantages. So if you look at that, the advantages of this light emitting diode, that is LED lighting device. So what actually it provides the benefits. So one thing, let's say for that matter, see the first as its life is concerned, see as compared to the all other traditional lamps which we have seen roughly like 6 months or up to at the most 3 years, uh, 2 years or up to 3 years. Okay. But otherwise, if we just look at this LED lifespan, it is it's really outstanding in its operational life. See, it's roughly like a 1 lakh hours. Uh, so that is the beauty of this the LED device. Okay, that takes the uh, very good part in this lighting system, and that is how, of course, this device it becomes uh, very prominent. Otherwise, see, but generally we see here in these LED lights, the mostly the failure is in the because almost all the time, see, once that we install this LED lamp, mostly we see that this flickering effect and blinking and this dimming, all these things, it is all not because of the failure of the LED device, but actually it is because of the failure of the circuitry elements, the in the that power driver circuit. That is what actually it's mainly what we are interested, and which concerns more for us. That power driver circuits. So means I mean to say the design of this power driver circuit to power this LED device, which is so-called LED lamp, is the most important thing. What it bothers us. And this energy efficient and estimated energy efficiency of like almost 80 to 90%, which is really, you know, the very outstanding figure. If you just look back to the other, the previous, the traditional, so there are like no very less, very poor efficiency as per that efficient. Okay. That means the major part of this energy consumed by this LED lamp is converted into the light output in terms of the luminous per watt. Okay, lumens per watt. So that is why. So we say this LED lamps consume a very less power as an input power source, but it provides the high significant output, huge output as a light output. Okay, in terms of the light output. Okay, so that is the beauty of these LED lamps. That is why these LED lights becomes so prominent and popular. Uh, in all variety of applications, almost all applications. Okay, and moreover, like these LED lamps, they are, of course, they are no, they don't have any like say coated with, or like which contains any kind of a harmful gases in this thing. They are purely like no, they are very free of these toxic gases, and so obviously they are quite friendly with respect to the environment and its disposal is concerned. Okay. And other aspect is that, so if you look, if we recall that fluorescent and HID lamps, generally they are not instant on and off. Okay, which is so happened in such lighting systems. because in the fluorescent lamps and HID lamps will so they have their own time, so to glit fully and also to turn off fully. That is what we used to experience that. Okay. Um, if at all, if you are happen to use such lamps, of course, you might be knowing very well about. That means even once you put on that light, immediately that light will not come into the full light stable operation, but it used to take its own time to okay um, come into this steady state operation, where in case of the fluorescent lamps and the HID lamps. But even such kind of issue is also not there here in this LED lighting systems. These lights can immediately, instantly, which can on and off. Okay, that means without affecting its light emission or like no affecting its lifetime lifespan of the device as well. So that means the instant on and off is possible, and that means even with the frequent high frequency of operations. Okay, that's fine. And the other thing is that operational condition is concerned. These are very ideal for this any kind of the environmental conditions, like even right from the very cold temperatures to the and for reasonably more at higher temperature in conditions also. So that way it is also very favorable. These devices are very favorable for all sort of condition, okay, atmospheric conditions. So that is another advantage. And uh, most importantly, as per this power consumption is concerned, this device which operates at very low operating voltage, that means it needs very low power supply, which is sufficient enough to power, okay, but to provide high bright light outcome. Means its operating voltage and current is even typically range from like hmm, 0.8 volts to even 3 volts. This operating voltage, even its typical operating current is roughly of uh, zero point 0.3 amperes. It is like that. But such a small device, okay, which can be used to configure the LED lamp right from the fractional wattage, even 0.5 watt to the hundreds of watts of this LED lamp. So that is possible with this very low operating voltage and current device, which is called light emitting diode. So that is these are the beauties of this advanced device, which is LED lighting device. Okay, and if you look at this is just the same thing what I have discussed, and but with some addition of two other information like the power consumption, energy consumption, and the power rating of these different lights. Just to understand, yes, uh, how significant improvement that we can see from this advanced lighting system uh, as compared to this traditional lighting resources. See, I think these aspects like lifespan and energy consumption, uh, instant turn on, turn off operation, which I have discussed, and this harmful toxic material. See, but that is only just that that comes with this fluorescent and HID lamps, but otherwise it's not a issue in this case. And other two aspect, what I was mentioning, it means that this LED lamp consumes a very less power as compared to the most traditional lamp. Suppose if you look at here, this is the incandescent bulb of a 60 watt bulb that can provide a light output of 12 lumens per watt. Okay, where the 13 watt, which is equivalent to even see, if you take the fluorescent lamp of 13 watt, and even this 13 watt fluorescent lamp, which is the improved version of this what is that this incandescent lamp, it means that almost like 5 times, 13 means roughly 5 times, 5 times reduced in this power rating of this fluorescent lamp. Even with that 5 times reduction in the power rating, but the what is that? Even this at the same time, the light outcome which provides with this fluorescent lamp is like 60 lumens per watt. It means that almost like even 5 times more light output. Okay, if you look at this traditional one, okay, that is the efficacy improvement with this improved version of the fluorescent lamp. Now, if we talk about the latest one, that advanced lighting system, which is called LED lighting systems. This is like no outstanding in all of this power consumption. See, just a 7 watt bulb. Even we cannot just compare with this any of these traditional versions like incandescent or this fluorescent lamp. So they consume, okay, almost say the 10 times more than this LED lamp, the power consumption. That means just a 7 watt LED lamp provides the light output, that is the lumens per watt, is up almost, okay, 110 lumens, which is almost the 10 times higher than that of this incandescent lamp, and almost double, 2 times higher than that of this fluorescent lamp. But why even with such a significant higher output of the light output of the system, that consumes the very less power, almost 10 times cut down, okay, less than that power consumed by these traditional ones. Like that is the advantage. Obviously, if that is the case, see, our energy bills will go significantly down. Okay, that is a point. So to exploit this kind of the huge outstanding benefits of this advanced light LED lighting system, we use for all the application. But however, here is the issue. In these, though they provide so many advantages. Mm, but still there are several issues which bothers us, especially by designing this the required power driver circuits for these LED lamps. That's the one thing. What is that one should understand. And typically what I was talking about, as the name itself, it indicates that there is a name diode, like light emitting diode. So it's typical operating behavior is just like a normal diode rectifier, what we have studied about. Okay, hence its name is also called like light emitting diode. So it means that it needs a cut-in voltage of like some voltage, that is so called operating voltage. So there onwards, it behaves just like a diode. Okay, that's why it is called like light emitting diode. Okay, and yeah, so as I was mentioning, its operating current and voltages are very low voltage and low current operate. Okay, roughly, of course, point. Okay, as a 20 milliampere to 1 ampere, even in the present market, which is available. Okay, like 2.3 to 4 volts. But however, though they operate at very small voltage and current, their luminous efficacy is tremendously high. That's the point. That is why, of course, we are just using that device for this lighting applications. And but however, here what we are talking about now, if this is the typical operating voltage and current of these LED devices. So, but we are talking about the LED lamps with the rating of like in terms of watts, like 5 watts, 10 watts, 20 watts, 60 watt, 100 watts, 200 watts, like that, depending on the type of applications which we prefer to use. Okay, but if that is the case, how these lamps are being designed? Suppose if I talk about just a simple 20 watt 20 watt LED lamp. Okay, operating voltage is 20 watts, and moreover, of course, another thing I guess I forgot to mention. And its operating voltage is of like a DC. It's not a AC voltage. Because obviously from the behavior of the switch device itself, we can understand, which is like a rectifier. Obviously, it's a unidirectional device, so it needs a direct current signal, that is a DC signal, DC voltage. It's not like a other AC voltage. So, but the providing this AC to DC at the required operating voltage level is one challenge, and at the same time, otherwise, the designing the lamps with the wide range of the power rating, depending on their, that again it mainly depends on this operating voltage and operating current. Of course, that we have the flexibility of design. But say typically, suppose if I consider a 20 watt 20 watt bulb, 20 watt LED bulb, say its operating voltage may be something like okay 20 volts, okay, or 24 volts per example. Say per example, this is just to understand. Okay, its operating voltage is 24 volts and its power rating is 20 watts. If that is the case, so how to design a power circuit for providing power to this 20 watt LED lamp with a the required operating voltage of 24 volts DC, which is required for that particular specific rating of the rated lamp. And this 20 watt bulb with the operating voltage of 24 volts, say for example, if it is like its operating voltage is something like one LED device is like 2.3 volts, say for example, and its operating current is roughly, say, if it is like 20 milliampere. Okay. So if that is, see, now here we have the catch to understand how this 20-watt bulb is designed with a small LED device with its operating voltage of 2.3 volts and operating current of 20 milliampere. So you mean to say this 24 volts is the total operating voltage, means the 24 volts is the this cutoff volt, the operating cut-in voltage which is required to operate your LED string. It means that if it is like 2.3 volts is the each device operating voltage, roughly like 10 devices, 10 LEDs. Okay. This 10 LEDs, LED device, each device of like, what is that? Um, 2.3 volts, like that. So, those many devices we keep in series. That is what it is being done in that LED PCB when they generally they prepare the LED lamp for a specific wattage. That means here the to fulfill the operating voltage of this this 24 volts, this 24 volts across that lamp, okay, 20-watt lamp. So it means that this that many number of LED devices which is being connected in series string. Okay, so this series string will perform the operating voltage. Now the point is see, if it is 20-watt bulb and operating voltage is 24 volts, what is the actual current carrying capacity of this lamp? It is roughly, so roughly it's something like 1 ampere, say for example approximately 0.9 amperes or 0.8 ampere. Okay, so if that is the case, but each string is capable of carrying 20 milliampere. 20 milliampere means like 0.02 ampere, right? If that is the case, so each string will have the operating voltage capability of 24 volts with a series string of 10 LED devices in each string. But each string can carry a current of 20 milliamperes. Okay, it means that 0.02 ampere typically. But to make this lamp to carry a total current, the total current drawn by your lamp to provide the 20-watt equivalent of light output, it's supposed to carry the around roughly 0.8, little approximately 0.8 ampere. So in order to provide in of the lamp, obviously this kind of a series string need to be put in parallel. Okay, put in parallel as many numbers as required. So depending on the total current requirement for that lamp. So that is how generally this the different wattage of this LED lamps is usually designed with. Okay, that PCBs. Okay, that is how. Okay, but that all is fine. It means that now if you look at this and the operating voltage of the LED lamp can be decided with like it's the total cutoff voltage and also the internal resistive drop which is expected here in this. Okay, in this diode. Okay, so this is how usually the total operating voltage of the LED lamp is usually designed. It's a typical steady state equation, and okay, that's to decide the operating voltage the any specific lamp. Okay, that and all it is fine, but however here is the issues in providing this such a small 24 volts operating one. No, that's just for example. Even there could be lamps with even less than the 24, even some 10 watts, 10 volts 10 volts lamp also may be there. See, it all depends depending on the rating of the lamp which comes with its operating. But however, to provide such a small DC voltage from from the AC grid of like this 220 volts. So that is the one thing one should understand. It means that as we know about see, we are all using nowadays almost all in every household, in every applications we use these LED lamps of very different ratings, right? But their operating voltages are usually of like a DC voltage and which is of very small voltage. Okay, as I mentioned. But how to provide such a small DC voltage from this a 220 volts AC grid? So that is the one important issue one should understand. Okay, it means that that clearly indicates an effective power conversion process from AC to DC, and also the DC to DC, the required voltage level to this LED lamp. Okay, these are the important point. Okay, things one should understand, and those things are need to be addressed in this effectively in this driver circuits. When what I so called like power converter ACD. Okay, AC/DC converters, especially for the grid fed LED lights. Most of our lighting systems are directly powered from our AC grid only. So therefore, providing this AC to DC conversion at the required safe operating voltage for the wide variety of LED lighting systems is the is the factors one should think, and those are the important ones one should address. Okay, and see what are the issues. Of course, anyway, we have seen the positive part, positive aspects of the this LED lighting systems so far in the discussion. But at the same time, to make use of those positive aspects of this LED lighting systems, uh, what are the issues that one also that we are supposed to face or to overcome while providing the effective driver circuit for this LED lighting system? That is the one thing one should understand, and which gives the even, of course, as a motivation for our research. Okay, most of us we are the academic teachers and the researchers. So obviously, when we are looking for this, the research aspects in these areas also. So there, of course, we have a huge scope in that, and therefore I say this is a motivation for research on this LED lighting system. This could be one direction. So what is the typical issues that we are supposed to be addressed in this lighting system, especially for these grid powered LED lighting systems? What I am talking about, there are like two issues, one from the source side, other from the load side. And from this load side is concerned, like it creates a issue of this low power factor issue. So what is this suddenly? Of course, if it is a low power factor means it indicates that though for the good benefit of this LED lighting system, we are using LED lights, but see, uh, we are trying to degrade the quality of power utilization from the grid. That's what this the indication of this low power factor issue on the source side. It means that, see, though we are being using this power for our purpose, and we should not create any issue to our power source. So that is, one should take care of that. That's like, no, our professional ethics and our responsibility. That means this power factor. How come this power factor is that the deterioration of power factor? That is one thing, and also that injection of the harmonics into the source side. So these two are the main problems which we. I think there is some noise. Could you please mute the?
Yes, sir. We have muted the participant, sir. Please continue, sir.
Okay, okay. See, yeah, these are the two problems which exhibit from the source side is concerned, main AC source is concerned. So those issues also we need to be taken care while designing the proper driver circuit. That is one thing. And as per the load side is concerned, load side is towards the lamp side, okay, in the design in the bridging the power converter and the LED lights that side. In this, there are several issues again. What is that like? Because this we are connecting this lamp to this AC grid of 50 hertz. Obviously, we see this in the final output, even after the conversion of AC, DC, and DC with after filter also. But even that filtered DC output is not purely DC. But again, we need to be no survive with a small ripple of with a frequency of the double the source frequency. That is so called, like we call it as a second order harmonic. Okay, which is trying to uh, 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 inject